Welcome as the day gently fades and the quiet of the night settles in. Allow yourself to sink deeply into whatever you're resting upon. Close your eyes and let go of the rigid structures of your waking hours. Tonight, we are setting out on a tranquil and boundless voyage through the corridors of time. We are going to explore the grand, unfolding tapestry of human thought, tracing the beautiful and deeply poetic story of mathematics. This is not a tale of harsh equations, rigid formulas, or cold, unfeeling logic. Rather, it is the magnificent story of how humanity slowly learned to understand the universe, the stars above, the earth below, and the delicate, repeating patterns of existence itself. For the next 2 hours, you have nowhere else you need to be. There are no problems you need to solve, no tasks you need to complete, and absolutely nothing you need to calculate. You are simply a quiet observer, drifting peacefully on the gentle and endless currents of history. As you listen to the sound of my voice, allow your breathing to naturally slow down. Take a slow, deep breath in, drawing in the calm of the night, and exhale softly, releasing any lingering tension. Let the ancient mysteries of the world carry you downward into a state of deep, restorative, and uninterrupted sleep. Our story begins long before the first stones of the first cities were ever laid upon the earth, and long before the first words were ever carved into clay or written on the parchment. It begins in the vast, untamed, and breathtakingly beautiful wilderness of the prehistoric world, taking root in the quiet, observant minds of our earliest ancestors. In the very beginning, there were no numbers. There was no concept of 1, 2, or 3. There was only the continuous present moment, the raw, unfiltered experience of a world that was both terrifying and magnificent. Yet the universe has always been a masterpiece woven from intricate patterns. The early humans, moving silently through the tall, whispering grass of ancient savannas, began to notice these recurring patterns long before they had the language to describe them. They noticed the stark difference between a single predator standing alone on the horizon and an entire pack moving together in the shadows. They observed the endless, rhythmic duality of day giving way to night and night yielding back to day. They watched the phases of the moon growing full and bright, only to shrink away into darkness in the night sky, and they felt the inevitable repetition of the seasons, the cyclical turning of warmth and cold, growth and decay. This silent observation was the very first whisper of mathematical thought in the human mind, the fundamental recognition of quantity. It was not a spoken word, nor was it a written symbol, but rather a silent, intuitive realization deep within the brain. It was the remarkable ability to look up at a vast flock of birds taking flight against a bruised purple sunset and understand intrinsically and without conscious thought the concept of many versus the concept of few. Before humanity could formally count, it possessed the profound ability to compare. The world was experienced and felt through the natural geometry of the earth and sky, the perfect glowing circle of the full moon, the sudden straight line of a falling raindrop slicing through the air, the intricate, endlessly repeating spirals of a nautilus shell resting quietly on a pristine, untouched beach. As thousands upon thousands of years drifted by, moving as slowly and inevitably as clouds across a prehistoric sky, the human mind began to seek a way to capture and hold on to these fleeting observations. They realized a deep, fundamental need to remember. They needed a way to record the passing of time, to track the cycles of the world around them, so they could anticipate what was to come. Deep in the heart of the Lubombo Mountains, a rugged and ancient range situated in what is now southern Africa, we find the earliest surviving physical evidence of this mathematical awakening. It is a small, unassuming, and weathered object, the fibula bone of a baboon, dating back an astonishing 40,000 years into the mists of antiquity. Carved into this hardened piece of bone are 29 distinct, deliberate, and carefully placed notches. 29 marks. The choice of this number was not random. The lunar month, the complete cycle of the moon from a sliver of new light to a brilliant full orb and back into darkness again, takes approximately 29 and a half days to complete. We can imagine a scene from 40 millennia ago, by the flickering, warm, amber light of a small campfire, while the rest of the world slept beneath a vast canopy of brilliant, unpolluted stars, and early humans sat in the quiet of the night. With deep concentration, they carefully scraped a sharp stone tool against the hard surface of the bone. One deliberate mark for each night that passed. One distinct groove for each time the moon rose into the dark sky. This simple act was a monumental leap forward in the evolution of human consciousness. It was the absolute birth of tallying. The unnamed individual who carved the Lubombo bone had successfully taken a massive, abstract, and intangible concept, the steady, flowing passage of time, and trapped it permanently in a solid physical form. They had instinctively created a one-to-one correspondence, which is the most foundational pillar of all mathematics. They forged a permanent link between a physical mark they could touch and an intangible moment in time that had already faded into memory. Moving further north through the ancient landscape, near the calm, reflective, and deeply still waters of Lake Edward in Central Africa, another astonishing artifact lay hidden and preserved in the rich earth for over 20,000 years, the Ishango bone. This ancient relic is far more complex and infinitely more mysterious than its predecessor in the Lubombo Mountains. The precise marks etched into the Ishango bone are not just simple, continuous tallies. Rather, they are grouped in highly specific, asymmetrical clusters and organized into distinct columns. Those who have devoted their lives to studying the bone have proposed many theories. Some believe it demonstrates an incredibly early understanding of multiplication and division. Others have pointed out that the numbers in one of the columns are all prime numbers, numbers divisible only by one in themselves. The true original intention of the ancient carver remains a silent secret, lost forever to the crushing weight of the ages. But what the Ishango bone tells us, without a single shadow of a doubt, is that the human mind was becoming increasingly restless, intensely inquisitive, and highly analytical. We were no longer simply surviving day to day in the wilderness. We were actively quantifying our existence. We were beginning the long and ambitious process of imposing a logical order onto the wild, chaotic beauty of the natural world. Time continued to flow onward, much like the great ancient rivers that shaped the surface of the earth. And it was exactly along the fertile banks of these massive, life-giving rivers that humanity finally began to cease its endless nomadic wandering and settle down into permanent communities. Seeds were deliberately planted into the dark soil, fields of crops were systematically harvested, and the very first permanent settlements began to slowly rise from the rich, wet mud. Here in the area often referred to as the cradle of civilization, nestled securely between the mighty, flowing currents of the Tigris and Euphrates rivers, the ancient Sumerians began the monumental task of building an entirely new world. As their small farming villages steadily grew into sprawling, complex mud brick cities, the day-to-day complexity of human life increased exponentially. A single farmer working the land no longer needed to merely keep track of enough food to feed their own immediate family. They now had to contribute specific amounts to central granaries, engage in complex trades involving herds of sheep and cattle, and pay calculated taxes to the massive temples that dominated the city skyline. The simple linear tally marks carved into pieces of bone or wood were no longer remotely sufficient to manage this bustling, overwhelming new reality of commerce and agriculture. The Sumerians desperately needed a robust and scalable system. Imagine standing in an ancient Mesopotamian marketplace just as the sun begins to rise. The morning air is cool and crisp, and the rich, earthy scent of damp clay and harvested grain fills the atmosphere. A merchant is in the process of finalizing a significant trade of livestock. To keep a permanent, unalterable record of this transaction, he does not use a pen and paper, for such things do not yet exist. Instead, he reaches down and takes a handful of wet, pliable clay straight from the riverbank. He rolls this clay between his palms until it forms a small, hollow sphere, a device known as a bulla. Inside this hollow clay sphere, he carefully places tiny geometric clay tokens. He might use a small cone shape to represent a small measure of grain, a perfectly round sphere to represent a much larger measure, or a small cylindrical token to represent a specific animal. The sphere is then sealed shut, locking the records safely inside. Eventually, the deeply practical Sumerians realized that instead of hiding the tokens away inside a sealed clay ball where they could not be easily seen, they could simply press the hard tokens directly into the soft exterior of a solid clay tablet to leave a clear, visible imprint of the shapes. And shortly after this realization, they took an even greater leap of abstraction. They abandoned the physical tokens altogether. They began using a wedge-shaped reed stylus, cut from the plants growing along the river, to draw the symbols directly onto flat, smooth clay tablets. This ingenious invention was the birth of cuneiform, recognized as the earliest known writing system in human history. It is a beautiful and poetic truth that the written word was not born from a desire to write poetry or record history, but was born entirely out of the strict mathematical necessity to count, to organize, and to meticulously record property and wealth. But the Sumerians did not merely stop at the invention of writing. They also invented an incredibly complex, fascinating, and enduring way of counting. Today in the modern world, we count in a base 10 system, which is almost certainly due to the simple biological fact that we possess 10 fingers on our hands. But when the ancient Mesopotamians looked down at their hands, their highly analytical minds saw something entirely different. They looked closely at the 4 fingers on one of their hands, and they noticed that each individual finger is naturally divided into 3 distinct segments, separated by the knuckles and joints. By using their thumb as a natural pointer, they could easily and rapidly count these individual segments. 3 segments on the index finger, 6 by the middle finger, 9 by the ring finger, and 12 by the pinky. By combining this clever base 12 counting method on one hand with the 5 individual digits on their other hand, they multiplied the 2 together and successfully created a sexagesimal system, a sophisticated counting system based entirely around the number 60. This base 60 system was an incredibly powerful and highly flexible mathematical tool. The number 60 is what mathematicians call a highly composite number. It can be divided perfectly and evenly by a vast array of numbers: 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This remarkable divisibility made dealing with fractions, percentages, and complex division remarkably easy and highly efficient for the ancient scribes. These dedicated individuals would sit for hours by the flickering light of oil lamps, carefully and quietly calculating the precise distribution of daily grain rations, projecting the exact yield of the upcoming harvest, and calculating the massive, staggering dimensions of their towering step ziggurats reaching up toward the heavens. Even right now, at this very moment, as you lie there resting in the quiet dark, slowly drifting toward a deep and peaceful sleep, you are still bound by the ancient mathematics of Babylon. Whenever you look at the face of a clock and see the 60 seconds ticking by in a minute, or the 60 minutes that make up an hour, you are directly observing the long, unbroken echo of a Sumerian scribe from over 5,000 years ago, quietly counting the segments of his fingers in the cool desert night. The very concept of a circle, universally divided into exactly 360 degrees, is a direct, enduring legacy of their meticulous astronomical calculations, created as they stood atop their temples and mapped the slow, majestic, and completely silent rotation of the starry heavens wheeling above them. As the brilliant mathematicians and scribes of Mesopotamia were quietly pressing their wedge-shaped styluses into damp clay, another completely distinct and equally brilliant civilization was slowly blooming to the west, nurtured by the slow, continuous flow of the longest river on earth. This was ancient Egypt. In the kingdom of Egypt, the entire rhythm of life was completely and utterly dictated by a single, monumental, and awe-inspiring natural event: the annual flooding of the mighty Nile River. Every single summer, functioning exactly like a deep, predictable, and rhythmic breath of the earth itself, the great river would swell with water and dramatically overflow its banks. It would spread out across the arid land, depositing a thick, rich, black layer of life-giving silt across the otherwise barren desert sand. This predictable flood brought the vital promise of life and agricultural prosperity, but it also brought a very specific and recurring mathematical challenge. When the dark flood waters eventually retreated back into the main channel of the river, the physical, earthly boundaries of the farmers' agricultural fields had been completely washed away and erased by the mud. The precious arable land had to be meticulously redistributed, the property borders had to be perfectly redrawn, and the critical taxes owed to the pharaoh had to be precisely calculated based on the exact area of flatland that each individual possessed. To solve this monumental annual problem, The highly resourceful Egyptians developed a deeply practical, incredibly visual, and hands-on form of mathematics. They became the world's very first true masters of geometry, a word that, when translated from its ancient roots, quite literally means the measurement of the earth. Imagine a vast open scene. The massive floodwaters of the Nile have just receded, leaving behind a blank canvas of dark, wet earth. The thick mud is slowly drying and cracking under the intense, baking heat of the North African sun. A specialized group of men, officially known and respected as the rope stretchers, walk out into the vast, flat, and featureless river valley. They carry with them long, heavy cords of thick rope, into which knots have been tied at highly specific and perfectly regular intervals. By physically stretching these heavy ropes across the mud, pulling them tight to form perfect triangles, squares, and rectangles on the ground, these men could recreate the exact precise boundaries of the agricultural fields with astonishing mathematical accuracy. The distances between the knots on these heavy ropes were not arbitrary. They were carefully measured and based on a profound underlying logic that forms the very foundation of geometry. By taking a long rope with knots spaced at exactly 3 units, 4 units, and 5 units, and pulling it completely taut, these ancient surveyors could form a perfect right-angled triangle upon the flat earth. This ingenious, deeply practical application allowed them to ensure that the corners of their vast agricultural fields, the massive stone blocks of their monuments, and the sprawling bases of their magnificent, towering temples were absolutely, flawlessly square. This application of mathematics was not a matter of abstract, philosophical debate for the Egyptians. It was an absolute necessity for survival, a way of maintaining cosmic order, and a physical manifestation of Ma'at, the ancient Egyptian concept of truth, balance, and universal harmony that governed all of existence. The highly educated scribes, sitting comfortably cross-legged in the cool, deep shade of the temple porticos, recorded these complex calculations with meticulous and unwavering care. Unlike their contemporaries in Babylon, they did not press a stylus into heavy clay tablets. Instead, they utilized the papyrus reeds that grew in thick, green abundance along the shallow banks of the river. They would harvest the tall stalks, peel away the rough outer layers, and slice the soft, pale inner pith into incredibly thin strips. These delicate strips were laid side by side, pressed tightly together, and left to dry under the intense, baking heat of the sun until they fused into a smooth, lightweight, and highly flexible writing surface. Upon these fragile, beautiful scrolls, using fine brushes made from chewed reeds and rich black ink crafted from soot and water, they carefully wrote down the mathematical wisdom of an entire empire. One of these magnificent scrolls, known today to historians as the Rhine Mathematical Papyrus, stretches out over 17 feet in length and contains a beautifully written, highly detailed collection of 85 different mathematical problems. As you sink deeper into your bed and let your muscles completely relax, try to imagine the deep, quiet concentration of the royal scribe named Ahmes, who carefully copied this very text over 3,500 years ago. In his beautiful, flowing script, he boldly proclaimed that this scroll was the true entrance into the knowledge of all existing things and all obscure secrets. Yet the secrets it actually contained were remarkably grounded in the daily, peaceful rhythms of ancient Egyptian life. The problems taught a young scribe how to evenly divide a specific number of loaves of baked bread among a large group of laborers. They detailed exactly how to calculate the precise amount of grain needed to brew a specific quantity of beer for a festival. They explained how to mathematically determine the exact slope, known as a seat, of a monumental pyramid to ensure that its massive, heavy walls rose perfectly and stably toward the heavens without collapsing under their own staggering weight. While the ancient Egyptians were deeply practical people, their mathematics was fundamentally infused with a profound sense of the sacred and the divine. When they dealt with fractions, parts of a whole, they relied almost entirely on what we now call unit fractions. These are fractions with a numerator of exactly 1, such as 1/2, 1/3, or 1/4. To visually represent these fractional parts in their daily records, they often use the rich mythological imagery of the Eye of Horus. According to ancient whispered legend, the eye of the powerful falcon god Horus was violently shattered into many pieces during a great cosmic battle. The god of wisdom, Thoth, magically and patiently reassembled the broken eye, piece by piece, restoring it to health. In Egyptian mathematics, the different distinct parts of the drawn eye represented different specific fractions of a whole. The inner pupil was exactly 1/4. The sweeping eyebrow was 1/8. The stylized teardrop falling below was 1/64. When added all together, the various pieces of the eye formed a complex fraction, yet they always fell just slightly short of a perfect, complete whole, representing the deep cultural belief that only the magic of the gods could ever make something truly and absolutely complete. This beautiful, seamless blending of religious myth and precise measurement allowed them to construct architectural structures of such breathtaking precision and massive scale that they continue to defy the slow, erosive, and relentless power of time itself. But as the centuries drifted quietly by, moving as slowly and inevitably as the endless dark waters of the Nile, the center of mathematical thought began to slowly, imperceptibly shift. We now leave behind the sun-baked sands of Egypt and the mud-brick ziggurats of Mesopotamia. We drift smoothly and gently across the calm, dark, azure waters of the Mediterranean Sea. The air becomes slightly cooler, carrying the gentle, refreshing scent of sea salt and wild green olive trees. We arrive on the rocky, indented, and beautiful coastlines of ancient Greece. Here, under a vast, open canopy of clear, brilliant blue sky, the human mind was about to perceive the concept of mathematics in an entirely new, deeply revolutionary light. In the bustling, wealthy port cities and the quiet, isolated island sanctuaries of the Aegean Sea, mathematics was about to undergo a profound and permanent transformation. It was no longer going to be merely a practical, earthly tool for measuring flooded fields, building massive stone tombs, or counting heavy sacks of harvested grain. It was about to become a pure, abstract quest for absolute, unshakable truth. It was about to become a philosophy. Imagine taking a slow, peaceful walk along the smooth, marble-paved streets of the wealthy Ionian city of Miletus in the 6th century before the Common Era. The evening air is warm and comfortable, filled with the soft, distant murmur of philosophical debate and the gentle lapping of the sea against the docks. Here lived a man named Thales, a wealthy merchant, a seasoned traveler, and a deep thinker who is widely remembered today as the very first true mathematician in the Western intellectual tradition. Before Thales, when humanity looked up at the turning stars or witnessed a powerful, frightening storm, they generally saw the unpredictable, chaotic whims of countless gods and unseen spirits. But Thales looked out at the natural world and saw a deeply logical, beautifully orderly structure. He firmly believed that the vast universe was governed by rational, unchanging laws, patterns that could be understood, predicted, and most importantly, logically proven by the power of the human mind. Legend softly tells us that during his extensive travels in Egypt, Thales stood in absolute awe before the magnificent, towering structure of the Great Pyramid of Giza. While the Egyptians had built it using their practical knotted ropes and physical measurements, Thales wanted to know its exact total height using nothing but the power of pure reason. He did not attempt to climb the massive, dangerous stone blocks, nor did he attempt to drop a long, heavy rope from the distant summit. Instead, he simply waited. He waited patiently in the quiet desert for the exact fleeting moment of the day when his own shadow, cast upon the golden sand by the afternoon sun, was exactly the same length as his physical body. With a quiet, brilliant flash of absolute insight, he reasoned that at that precise moment in time, the immense dark shadow cast by the towering pyramid must also be exactly equal to its true physical height. He used the pure, intangible geometry of sunlight to solve the ancient mystery. This was a profound, earth-shattering shift in the history of human thought. It was the birth of deductive reasoning. Thales was no longer satisfied with simply knowing that a mathematical rule or a measurement worked in practice. He demanded to know exactly why it worked. He insisted on absolute logical proof, a deeply radical concept that would forever change the trajectory of human intellectual history and the way we understand our reality. As we drift further along the gentle, slow-moving currents of this golden age of thought, we encounter a figure whose name still echoes brightly in every quiet classroom around the world today: Pythagoras of Samos. But Pythagoras was not just a mathematician in the strict modern sense of the word. He was a deeply mystical thinker, a highly charismatic philosopher, and the revered, unquestioned leader of a highly secretive ascetic brotherhood. This dedicated brotherhood lived together in a quiet, secluded, and peaceful community, strictly bound by solemn vows of absolute loyalty and unbroken silence. For the Pythagoreans, mathematics was not just a tool, it was a religion. They firmly and passionately believed that the entire universe, in all of its vast, breathtaking, and overwhelming complexity, was fundamentally constructed from pure whole numbers and the simple, elegant ratios between them. To these ancient thinkers, numbers were not just arbitrary symbols written in the dust of the earth. They were the pure, incorruptible, and divine essence of reality itself. Imagine sitting quietly in a peaceful, open-air, moonlit courtyard within the ancient coastal city of Croton, where the Pythagorean Brotherhood eventually made their home. The night is perfectly still, the air is cool, and the only sound is the gentle, rhythmic, and soothing plucking of a single-stringed musical instrument known as a monochord. Pythagoras, through careful, quiet, and deliberate experimentation in the dark, made a staggering and beautiful discovery. He found that when you pluck a tense, physical string, the exact pitch of the musical sound it produces depends entirely and mathematically on its physical length. But far more importantly, he discovered that if you press your finger down perfectly in the dead center of the string, dividing its length exactly in half, it produces the exact same musical note, just one perfect octave higher. It is a pure, flawless mathematical ratio of 2-to-1. If you divide the string into thirds or into fourths, you create beautifully harmonious, incredibly pleasing chords that resonate perfectly and peacefully with the human ear. For the Pythagoreans, and this was a blinding revelation of absolute cosmic proportions. The beautiful, soothing, and relaxing music filling the cool night air was not just a subjective art form, it was pure mathematics, made suddenly and vividly audible to the human senses. They believed with every fiber of their being that this profound mathematical harmony extended far beyond the walls of their small courtyard, stretching out into the vast turning heavens above. They believed that the massive planets themselves, as they moved in perfect, circular, and eternal orbits through the velvet darkness of deep space, literally hummed with this exact same mathematical harmony. They imagined a magnificent ongoing celestial music of the spheres, a continuous, perfect, and flawless symphony that was simply too vast, too deep, and too profound for the mortal human ear to ever truly hear. As you lie there, close your eyes for a moment and simply imagine that silent, cosmic symphony turning slowly, perfectly, and endlessly in the infinite, comforting darkness above you. To the devoted Pythagoreans, this beautiful, orderly, and highly predictable universe of whole numbers was a source of deep peace, ultimate truth, and profound spiritual comfort. But this flawless, shimmering mathematical worldview hid a dark, chaotic, and deeply unsettling secret beneath its perfect surface. It was the secret of the incommensurable, the terrifying discovery of the irrational number. The ancient story goes that a devoted and curious member of the Brotherhood, a man named Hippasus, was quietly investigating the properties of a very simple, everyday geometric shape, the square. If you draw a perfect square in the sand, where each of the four sides is exactly 1 unit long, how long is the diagonal line that cuts straight across the center from one corner to the opposite corner? According to the famous Pythagorean theorem itself, the square of this diagonal line must be equal to the number 2. Therefore, the exact precise length of the diagonal must be the square root of 2. But when Hippasus sat in the quiet shade of an olive tree and attempted to write the square root of 2 as a simple fraction, as a neat, tidy, and perfect ratio of two whole numbers, he found that it was mathematically impossible. No matter how large the numbers he used, no matter how long he painstakingly calculated, the numbers spiraled on forever, stretching out without any repeating pattern, without any logic, and without any end, diving straight into the terrifying and boundless depths of infinity. It was an irrational number. It simply could not be expressed as a perfect ratio. According to whispered legend, this shocking discovery so deeply horrified the Pythagoreans that Hippasus was sworn to absolute unbreakable secrecy, or perhaps even thrown into the sea, for his discovery threatened to completely shatter the very foundation of their perfect, harmonious, whole number universe. It is a gentle, lingering reminder that the universe always holds profound, unfathomable mysteries just beyond the very edge of our current understanding, quietly inviting us to look deeper, to question further, and to expand our minds into the peaceful unknown. The unsettling discovery of the irrational number did not stop the human mind from reaching further into the abstract heavens. If anything, the terrifying and boundless concept of infinity only served to deepen the profound mystery of mathematics, pulling philosophers further away from the physical dirt of the earth and deeper into the endless landscapes of pure thought. As the initial shockwaves of the incommensurable slowly settled over the Greek world, another brilliant mind stepped forward to gently challenge the very nature of space, time, and motion. In the quiet, sun-drenched coastal town of Elia, a philosopher named Zeno began to craft a series of deep, mesmerizing puzzles that would quietly haunt the minds of mathematicians for thousands of years to come. These were not rigid equations to be solved with a stylus on a wax tablet, but tranquil, mind-bending paradoxes designed to show that our physical senses, the very eyes we use to look at the world, might be entirely deceiving us. Imagine standing on a quiet, dusty path, looking ahead and deciding to walk toward a beautiful, distant olive tree. Zeno proposed a beautifully simple, hypnotic thought experiment. He reasoned that to reach that distant tree, you must first travel exactly half the distance to get there. That is a logical, undeniable truth. But once you have reached that halfway point, you must then travel half of the remaining distance. And once you reach that new point, you must again travel half of the small distance that is left. You can continue dividing that remaining space in half forever and ever, creating an infinite, endless series of microscopically shrinking distances. Therefore, Zeno argued in a soft, profoundly persuasive voice, motion itself must be a beautiful, elaborate illusion. You can never truly arrive at the tree because you must always cross an infinite number of halfway points, gently slowing down, getting closer and closer, slipping infinitely through space, but never truly touching your final destination. He created another famous paradox, a gentle race between the great fleet-footed warrior Achilles and a slow, lumbering tortoise. If the tortoise is given a slight head start, Zeno argued that the swift Achilles could never, ever overtake it. By the time Achilles reaches the point where the tortoise began, the tortoise has moved a small distance forward. By the time Achilles crosses that new, smaller distance, the tortoise has moved forward again, just a tiny bit more. The gap between them infinitely shrinks, becoming smaller than a grain of sand, smaller than a whisper, but logically, mathematically, the gap can never truly be closed. These gentle, profound paradoxes about the infinite divisibility of space and time wrap the Greek mathematical world in a soft blanket of philosophical doubt. They demonstrated that logic and mathematics were not just tools for measuring things you could touch, but were powerful instruments capable of completely unraveling the fabric of reality itself, exposing the strange, infinite depths that lie quietly beneath the surface of the physical world. As the years drifted softly by, the absolute epicenter of this intellectual revolution shifted away from the isolated coastal towns and the secretive brotherhoods, moving slowly toward the bustling, magnificent heart of ancient Greece. We drift now into the beautiful, intellectual atmosphere of Athens. Imagine walking away from the noise of the city markets, leaving the heavy stone temples behind, and wandering into a peaceful, deeply shaded grove of ancient olive trees just outside the city walls. The air here is remarkably still, filled only with the soft rustling of silver-green leaves and the quiet murmur of deep, focused conversation. This is the academy founded by the great philosopher Plato. Above the entrance to this tranquil sanctuary of learning, a simple, strict, and powerful warning was allegedly carved into the stone. Let no one ignorant of geometry enter here. For Plato, mathematics was far more than just a subject to be studied. It was the ultimate necessary purification of the human soul. He believed with absolute conviction that the physical world you can see, touch, and hear is nothing more than a messy, flawed, and constantly decaying shadow of a much higher, perfect reality. He famously asked his students to imagine a group of prisoners chained inside a dark, quiet cave, facing a blank wall. Behind them burns a warm fire, and between the fire and the prisoners, various objects are carried past. The prisoners can only see the flickering shadows cast upon the wall, and they mistakenly believe that these flat, distorted shadows are the true reality. Plato taught that our daily, physical lives are exactly like watching those shadows. But mathematics, he argued, is the brilliant, blinding light of the fire itself. When you draw a circle in the wet sand, no matter how carefully you trace the line, it will never be completely, flawlessly round. The sand is uneven, your hand trembles ever so slightly, and the line has physical thickness. But the concept of a circle, the pure, abstract, mathematical idea of a set of points perfectly equidistant from a center, exists in a state of absolute eternal perfection. It never changes, it never decays, and it is entirely untouched by the slow ravages of time. By turning the mind away from the messy shadows of the physical world and quietly contemplating these perfect, flawless mathematical forms, Plato believed the human soul could gently ascend to a state of absolute peace, ultimate enlightenment, and divine understanding. This deep reverence for pure geometry reached its absolute pinnacle in the discovery and reverence of the Platonic solids. Imagine, in the quiet theater of your mind, a series of perfect, flawlessly symmetrical three-dimensional shapes slowly rotating in an infinite dark void. In all of mathematics, in all the possible configurations of the universe, there are only 5 perfect, regular polyhedrons, shapes where every single face is the exact same regular polygon and every single corner is perfectly identical. There is a tetrahedron built of 4 perfect triangles, sharp and pointed, which Plato associated with the hot, rising nature of fire. There is the hexahedron, or the cube, perfectly stable and grounded with its 6 square faces, representing the solid, immovable earth. There is the octahedron, with 8 triangular faces, smooth and aerodynamic, representing the invisible flowing air. There is the icosahedron, a beautiful, complex shape made of 20 triangles, rolling easily like a drop of water, representing the fluid oceans. And finally, there is the most mysterious and beautiful shape of them all, the dodecahedron, constructed of 12 perfect, identical pentagons. Because it was so close to a perfect sphere, yet built of complex, rigid geometry, Plato and his followers believed this final shape represented the divine ether, the magical, invisible substance that made up the cosmos itself, the shape the gods used to organize the constellations in the dark night sky. To study these 5 perfect shapes was to look directly into the mind of the Creator, to see the hidden, geometric blueprints of the universe slowly turning in the dark. It was a mathematics of pure, unadulterated beauty, completely divorced from any practical need to measure a field or count a coin. It was mathematics as a form of deep, spiritual meditation. But the boundless energy of the Greek mind could not remain forever in the abstract, shadowless realm of Plato's ideal forms. The human desire to organize, to categorize, and to build a solid foundation of undeniable truth led to the creation of something entirely new and breathtakingly powerful: formal logic. This monumental task was taken up by Plato's most famous student, Aristotle. While he respected the beautiful geometries of his teacher, Aristotle was driven by a deep need to ground human reasoning in a set of unbreakable, step-by-step rules. He wanted to understand not just what was true, but exactly how we could prove it was true without a single shadow of a doubt. He developed the syllogism, a form of quiet, precise, and flawless deduction. If you accept a major premise and you accept a minor premise, then a specific, unavoidable conclusion must naturally and smoothly follow. This gentle, rhythmic stepping stone of logic, if this is true and that is true, then this third thing must absolutely be true, became the steady heartbeat of all future mathematics. It was a comforting, solid structure. It meant that a mathematician did not have to rely on intuition or divine inspiration or the mystical beliefs of a secretive brotherhood. They only needed a starting point in the quiet, rigorous application of logical steps. It was a way of building a long, unbreakable chain of truth, a safe and secure pathway through the dark, unknown forests of human ignorance. As the centuries gently turned, the golden age of Athens slowly began to fade, and the great epicenter of human knowledge shifted once again, carried on the warm winds across the Mediterranean Sea. We drift away from the olive groves of Greece and arrive on the vast sandy shores of northern Egypt, where a brand new, magnificent city was rising from the earth. Alexandria, founded by Alexander the Great, this sprawling, incredibly wealthy metropolis was designed to be the intellectual beacon of the entire ancient world. And at its very heart, surrounded by beautiful gardens, quiet walkways, and the gentle sound of flowing fountains, stood the Great Library. Imagine walking into this vast, quiet sanctuary of knowledge. The air is cool and smells faintly of dry papyrus, old dust, and beeswax. The walls are lined with endless rows of wooden shelves, holding hundreds of thousands of tightly rolled scrolls, containing all the accumulated wisdom, history, and mathematics of the known world. It was a place of deep, profound silence, broken only by the soft rustling of unrolling papyrus and the quiet scratching of reed pens. In this peaceful haven of thought, surrounded by the greatest scholars of the age, lived a man named Euclid. Euclid accomplished something so monumental, so perfectly structured, and so incredibly beautiful that his work would go on to become the single most successful and widely read textbook in the entire history of human civilization. He gathered all the scattered, disconnected geometric knowledge of the Egyptians, the Babylonians, the Pythagoreans, and the Platonists. He laid out all these fragments of truth, and then, with unimaginable patience and brilliant clarity, he wove them together into a single, flawless, and unified masterpiece known simply as the Elements. Reading Euclid's Elements is like slowly exploring a grand, perfectly proportioned cathedral of the mind. He understood, thanks to the logic of Aristotle, that you cannot prove everything. If you try to prove every single statement, you will endlessly fall backward into an infinite loop of definitions. To build a solid structure, you must start with a foundation of things that are simply accepted as true. Euclid called these starting points axioms, or common notions. These were simple, quiet, deeply comforting truths that were so obvious, so intuitively self-evident, that they required absolutely no proof. Imagine sitting in the quiet library with Euclid as he gently lays out these 5 foundational seeds of reality. First, he stated that you can draw a straight line between any 2 points. Second, that you can extend that straight line infinitely in either direction. Third, that if you have a center point in a distance, you can draw a perfect circle. Fourth, that all right angles are exactly equal to one another. These were peaceful, undeniable statements, as solid and dependable as the ground beneath your feet. But it was his 5th axiom, the famous parallel postulate, that was slightly more complex, a beautiful puzzle that would quietly fascinate mathematicians for millennia. He stated that if you have a straight line and a point perfectly suspended somewhere in the empty space beside it, there is one and only one straight line that can be drawn through that point that will never, ever intersect with the first line, no matter how incredibly far they are extended into the infinite darkness of space. They will run side by side, perfectly parallel, forever. From these 5 humble, incredibly simple seeds, Euclid used nothing but pure, unadulterated logical deduction to grow a massive, sprawling, and breathtakingly complex forest of mathematical truth. Step by step, theorem by theorem, he proved the properties of triangles, the areas of circles, the nature of prime numbers, and the construction of the 5 Platonic solids. He built an entire universe of absolute certainty. In a world that is often chaotic, unpredictable, and frightening, the geometry of Euclid provided a sanctuary of absolute, unshakable order. Once a theorem was proven in the Elements, it was proven forever. It was a truth that was immune to the changing of the seasons, the rise and fall of empires, and the slow, inevitable fading of human memory. It is a profoundly comforting thought to hold on to as you rest, that there exists a realm of pure, flawless logic, where truth is permanent, where lines run perfectly straight into infinity, and where everything makes absolute, beautiful sense. While Euclid was meticulously building his unshakable cathedral of logic within the quiet, cool walls of the Great Library, the brilliant minds of Alexandria were also turning their attention outward, looking past the abstract forms of geometry and applying their mathematics to the massive physical scale of the planet itself. Imagine walking through the shaded courtyards of the library, the air thick with the scent of blooming jasmine, in the distant rhythmic sound of the Mediterranean waves. Here we meet a man named Eratosthenes, a scholar of boundless curiosity who served as the chief librarian. Eratosthenes accomplished something that seems almost like magic. Using nothing more than a simple wooden stick, his own peaceful shadow, in the pure, flawless geometry of Euclid, he accurately measured the entire circumference of the Earth. The story is a masterpiece of quiet, patient observation. Eratosthenes had read in one of the thousands of scrolls that in the southern city of Syene, located near the modern city of Aswan, a beautiful and extraordinary event occurred exactly on the summer solstice, the longest day of the year. At the precise moment of high noon, when the sun was at its absolute zenith, the columns of the temples cast no shadows whatsoever. The sunlight plunged straight down into the deepest water wells, illuminating the water at the very bottom. The sun was exactly perfectly overhead. But Eratosthenes noticed that on that exact same day, at that exact same moment of high noon, in his own city of Alexandria far to the north, the obelisks and sundials did cast a shadow. The sun was not directly overhead, it struck the earth at a very slight angle. A lesser mind might have simply ignored this minor detail. But Eratosthenes possessed a deep mathematical intuition. He realized that this difference in shadows was the undeniable proof that the surface of the earth was gently, continuously curving beneath their feet. With profound tranquility and focus, he measured the exact angle of the shadow cast in Alexandria, finding it to be about 7.5 degrees, or roughly 1/50th of a perfect circle. He then hired specialized pacers, men whose sole profession was to walk with a perfectly consistent, even stride. To walk the vast, dusty distance from Alexandria all the way south to Syene. By multiplying that long, arduous distance by 50, Eratosthenes calculated the total massive circumference of the globe. As you rest in the quiet dark, let your mind float high above the earth. Imagine looking down upon the great sphere of our world, drifting silently through the velvet blackness of space. Thousands of years before humanity would ever leave the ground, a single man, sitting quietly with a piece of parchment in a shadow, wrapped his mind entirely around the planet. Across the sparkling blue waters of the sea, on the rugged, beautiful island of Sicily, another mind was pushing the boundaries of mathematics even further into the infinite. We return to the coastal city of Syracuse, the home of Archimedes. Archimedes was a man so deeply consumed by the peaceful beauty of numbers that the physical world around him often simply faded away into a soft, meaningless blur. He did not just want to measure the earth, he wanted to measure the entire universe. In a beautiful, poetic manuscript called the Sand Reckoner, Archimedes set out to solve a problem that most people considered absolutely impossible. He wanted to calculate exactly how many grains of tiny, microscopic sand it would take to completely fill the entire known universe. To the average person walking along the beach, feeling the countless grains of sand beneath their feet, the number was simply infinite. It was too vast to be named, too massive to be comprehended. But to Archimedes, nothing was beyond the reach of mathematics. To accomplish this staggering feat, he first had to invent an entirely new way of naming massive numbers. A system capable of reaching far beyond the traditional counting limits of the ancient Greeks. He carefully estimated the size of a single grain of sand. He then calculated how many grains would fit into a small seed, how many seeds would fit into a standard measurement, and so on, building upward in massive exponential leaps. He expanded his calculations to fill the size of the Earth, then the distance to the sun, and finally he expanded his imaginary sphere of sand to reach the distant fixed stars. The final number he arrived at was unimaginably massive, a number we would write today as an 8 followed by 63 zeros. But the actual number itself was not the true triumph. The true lasting beauty of the Sand Reckoner was the profound realization that the human mind could gently and logically tame the infinite. No matter how incredibly vast the universe was, no matter how small and insignificant a single grain of sand might seem, the quiet power of mathematics could encompass it all. It is a deeply soothing thought that there is no chaos so vast, no space so deep that it cannot be understood, measured, and brought into perfect, harmonious order. Archimedes spent his final days doing exactly what he loved most. The story tells us that when the Roman army finally breached the walls of Syracuse after a long exhausting siege, Archimedes was an old man, sitting quietly in a sunlit courtyard. He was completely absorbed in contemplating a series of geometric circles he had drawn in the dust of the floor. He was deeply at peace, entirely disconnected from the violence and noise of the physical world collapsing around him. When a Roman soldier approached him and demanded his attention, Archimedes did not look up. He simply raised his hand, completely undisturbed, and softly requested that the soldier not disturb his circles. His mind was resting securely in a higher, eternal realm of pure truth, untouched by the fleeting struggles of empires. As the mighty Roman Empire slowly expanded, wrapping its vast roads and aqueducts around the Mediterranean, the golden creative light of Greek mathematics began to softly dim. The Romans were brilliant engineers, master builders of domes, bridges, and colosseums, but they were deeply pragmatic. They were interested in the practical application of numbers to build walls and collect taxes, not the gentle philosophical contemplation of infinity or the perfect forms of Plato. For centuries, the deep theoretical advancements in geometry and logic slowed to a quiet, resting pause in the West. The final, beautiful flicker of the ancient Greek mathematical spirit burned in the city of Alexandria, guarded by a remarkable woman named Hypatia. She was a brilliant philosopher, a master astronomer, and the head of the Neoplatonic school. In a time when the world was becoming increasingly fractured and chaotic, Hypatia stood as a beacon of calm, rational thought. She dedicated her life to preserving, editing, and teaching the great works of Euclid and the ancient astronomers. Imagine her in the vast echoing halls of the library late at night, a single oil lamp illuminating the ancient scrolls as she carefully copied and refined the mathematical heritage of humanity, ensuring that the light of reason would not be completely swallowed by the encroaching shadows. But the world was changing. The great libraries were eventually destroyed, their irreplaceable scrolls burned or lost to the damp rot of time. The grand sweeping era of classical antiquity, with its perfect circles and absolute axioms, slowly closed its eyes and drifted into the long, dark sleep of history. However, the beautiful story of mathematics was far from over. The profound knowledge of the ancients was not entirely lost. It was merely resting, waiting to be awakened in a different land. As the West fell into the quiet slumber of the early Middle Ages, the vital seeds of mathematical thought were quietly carried eastward, traveling along the long, winding, and dusty paths of the Silk Road. They moved across vast, silent deserts and over towering, snow-capped mountain ranges, finally arriving in the lush, vibrant, and deeply spiritual subcontinent of India. Here in the shadow of the Himalayas and along the sacred flowing waters of the Ganges River, mathematics was about to experience a profound rebirth. The Indian mathematicians did not just preserve the geometry of the Greeks. They approached the universe with a completely different philosophical lens. While the Greeks were deeply obsessed with geometry, with shapes, lines, and physical space, the Indian thinkers possessed a profound mastery of numbers themselves, of arithmetic and the vast abstract nature of calculation. To understand the mathematics of ancient India, you must first understand their deep, enduring cultural connection to the infinite and the void. In Indian philosophy and religion, the universe operates on unimaginable scales of time. They calculated cosmic cycles, known as yugas, that span millions and billions of years, time frames so vast that they dwarf the entire lifespan of the Earth. To deal with these staggering cosmic numbers, they needed a counting system that was incredibly powerful, flexible, and elegant. And so they gave the world one of the greatest, most profound gifts in the entire history of human civilization, the Hindu-Arabic numeral system. Until this moment, people counted using cumbersome tally marks or the complex, unyielding letters of the Roman numeral system. If you try to multiply large Roman numerals together, it is a chaotic, frustrating puzzle. But the scholars of India developed a beautiful, simple system using only 10 distinct symbols, including the numbers 1 through 9. More importantly, they invented a system of place value where the physical position of a digit changes its magnitude. A single symbol could represent a 1, a 10, or a million simply based on exactly where it sat in the silent, invisible columns of a number. But this beautiful system of place value required one final magical key to work perfectly: It required a symbol for something that the ancient Greeks had actively feared and rejected. It required a symbol for nothing. The Greeks believed that if something did not physically exist, it could not be mathematically measured. How can you have a shape of nothing? How can you have a geometry of empty space? But the Indian philosophers deeply embraced the concept of the void. They called it shunya, a beautiful Sanskrit word that translates to emptiness, or the quiet, peaceful void that exists before creation and after destruction. It is the absolute stillness of a mind in deep meditation, the perfect, tranquil silence when all the chaotic thoughts of the day have finally faded away. They took this profound philosophical concept of nothingness and gave it a physical, mathematical shape. They drew a simple, continuous dot, which eventually evolved into a perfect, hollow circle, zero. The invention of zero was the moment mathematics truly woke up. By creating a number that represented absolutely nothing, they paradoxically made everything else possible. Zero acts as the silent, unmoving anchor in the flowing river of numbers. It holds the empty columns open, allowing the ones, tens, and hundreds to align perfectly, making complex multiplication, division, and the future calculation of the cosmos beautifully effortless. As you drift deeper into the night, think of the concept of shunya. Allow your own mind to gently approach that state of zero. Let go of all the complicated equations of your day, release the heavy numbers of your waking life, and allow yourself to slowly dissolve into the deep, peaceful, and perfect void of a dreamless sleep. The profound invention of zero, the mathematical embodiment of the peaceful void, did far more than simply hold open the empty columns of a number. It fundamentally and permanently altered the landscape of human thought, opening the door to concepts that would have terrified the ancient Greeks. As you lie resting in the quiet dark, let your mind linger in the vast starlit observatories of ancient India and the thriving city of Ujjain during the 7th century. Here, surrounded by intricate instruments designed to measure the slow, majestic transit of the planets, lived a brilliant astronomer and mathematician named Brahmagupta. He was a man deeply in tune with the rhythmic cycles of the cosmos, spending his nights gazing upward into the velvet blackness of the sky. In a monumental text, he did something entirely unprecedented. He treated zero not just as a blank space, but as a true independent number. He established the quiet, logical rules for how this concept of nothingness interacted with the physical world. He wrote down the rules of addition, subtraction, and multiplication involving zero, creating a perfectly balanced arithmetic of the void. But Brahmagupta's mind reached even further into the abstract unknown. By fully embracing the concept of zero, he realized that numbers did not actually have to stop when they reached nothing. The ancient world had always believed that you could not have less than nothing. If you had 3 apples and took 3 away, you had 0, and that was the absolute impenetrable floor of reality. But Brahmagupta envisioned a mathematical universe that extended downwards, below the surface of the visible world. He introduced the revolutionary concept of negative numbers. To explain this radical idea, he used the simple, everyday language of fortunes and debts. A positive number was a fortune, something you physically possessed. A negative number was a debt, a deeply abstract concept of something you owed, a number that existed entirely in the realm of human agreement rather than physical reality. Imagine a massive ancient tree standing quietly in a dense, peaceful forest. The ancient Greeks, with their geometry of physical shapes, only measured the trunk and the branches extending upward into the bright, visible sunlight. These are the positive numbers. But Brahmagupta realized that for the tree to stand tall and perfectly balanced, it must possess an equally massive hidden network of roots extending deep downward into the cool, dark, unseen earth. These roots, reaching into the silent depths below the surface, are the negative numbers. They are the mirror image of the world above. By creating negative numbers, Brahmagupta effectively doubled the size of the mathematical universe. He created a vast, infinite number line that stretched endlessly forward into the positive light and infinitely backward into the quiet, dark depths, with zero resting perfectly and peacefully in the absolute center, a fulcrum upon which the entire cosmos balanced. This deep, intuitive understanding of balance and cosmic rhythm also led the mathematicians of India to revolutionize the way humanity measured the heavens. While the Greeks had looked at the stars and tried to map them using rigid, straight chords drawn inside circles, the Indian astronomers developed a much more elegant, fluid, and natural system. They created the foundations of what we now call trigonometry. A brilliant scholar named Aryabhata, working in the 5th century, looked at the smooth, curved arc of the sky and realized that measuring the universe required a mathematics that flowed like water, rather than one that snapped like a rigid stick. He developed the concept of the sine function, which in ancient Sanskrit was called jya or jiva, meaning the gentle curve of an archer's bowstring. Instead of dealing with whole clunky shapes, the sine function allowed astronomers to measure the smooth, continuous, and rhythmic relationships between angles and distances. As the Earth slowly turns and the stars wheel across the night sky in their endless circular dance, their apparent motion can be mapped using these beautiful, undulating sine waves. Think of a sine wave right now. Picture a smooth, continuous line gracefully rising to a gentle peak, then softly falling back down into a valley, only to rise again in perfect, unbroken repetition. It is the exact rhythm of a pendulum swinging quietly in a grandfather clock. It is the exact rhythm of a slow, rolling ocean wave gently breaking upon a distant shore. And most importantly, it is the exact peaceful rhythm of your own breathing as you drift towards sleep. The slow, steady rise and fall of your chest, mirroring the fundamental mathematics of the turning universe. As the centuries quietly passed, this profound flowing mathematics of India, with its flexible place values, its mysterious zeros, and its deep negative roots, began to slowly travel. It did not move through war or conquest, but along the slow, quiet, and dusty pathways of the ancient trade routes. The knowledge was carefully written onto fragile manuscripts and tucked safely inside the leather saddlebags of merchants. Imagine a long, peaceful caravan of camels walking with a slow, hypnotic, and rhythmic sway across the vast, undulating sand dunes of the Silk Road. The sun beats down, casting long, shifting shadows across the desert floor, as the accumulated wisdom of the East slowly makes its way westward, drawn toward the rising wealth and intellectual hunger of the rapidly expanding Islamic Empire. We now drift away from the shadow of the Himalayas and arrive in the magnificent, sprawling city of Baghdad during the 8th and 9th centuries. This was the absolute height of the Islamic Golden Age, a time when Baghdad was the wealthiest, most advanced, and most intellectually vibrant city on the entire planet. It was known as the Round City, built in a series of perfect, concentric geometric circles alongside the flowing, life-giving waters of the Tigris River. At the very center of this bustling metropolis, surrounded by lush, green, fragrant gardens and the soothing, constant murmur of running fountains, stood a magnificent institution known as the Beit al-Hikmah, the House of Wisdom. The House of Wisdom was not just a library, it was a massive, dedicated translation center and an academy of pure thought. The Abbasid caliphs, deeply devoted to the pursuit of knowledge, sent emissaries to the farthest corners of the known world with a simple, singular mission: find every book, every scroll, and every fragment of ancient wisdom and bring it back to Baghdad. Imagine walking through the cool, shaded arches of this grand building. The air is heavy with the scent of old paper, rich black ink, sweet mint tea, and burning frankincense. In the vast, quiet reading rooms, scholars of every faith and background, Muslims, Christians, Jews, and Zoroastrians, sat side by side in absolute peace. They were engaged in a monumental, painstakingly slow labor of love. They were translating the ancient Greek geometry of Euclid and the vast astronomical tables of India into a single unified language, Arabic. It was within these quiet, scholarly walls that the two great rivers of ancient mathematical thought finally merged into one magnificent ocean. The rigorous, visual, and logical geometry of the Greeks was seamlessly combined with the abstract, flexible, and powerful numerical arithmetic of the Indians. And from this beautiful synthesis, a completely new branch of mathematics was quietly born, crafted by the mind of a brilliant Persian scholar who worked in the House of Wisdom. His name was Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi recognized that while Greek geometry was beautiful, it was deeply tied to physical shapes. If a Greek mathematician wanted to solve a problem, They had to painstakingly draw squares and rectangles in the sand. Al-Khwarizmi wanted to create a mathematics that was completely free from the physical world, a pure abstract system of logic that could solve any problem, regardless of what that problem was about. He wrote a revolutionary book with a long poetic title, The Compendious Book on Calculation by Completion and Balancing. In Arabic, the word for completion, the act of restoring something broken to its whole and perfect state, is algebra. This single word, algebra, would slowly echo across the centuries and evolve into the word we know today as algebra. Algebra is often misunderstood as a frustrating puzzle of letters and numbers, but in its purest, original form, it is one of the most deeply calming and therapeutic concepts in all of human thought. Algebra is the mathematics of the unknown. In life, we are constantly faced with situations where we do not have all the answers, where there is a missing piece, a hidden variable that we cannot immediately see. This unknown can often cause anxiety and confusion. But Al-Khwarizmi taught the world that you do not need to fear the unknown. You simply need to give it a name. Embrace its presence and treat it with the same respect as the things you already know. Imagine a beautifully crafted antique brass balancing scale resting on a wooden table. It has two small bowls suspended from a central beam. Algebra is the quiet and methodical process of keeping that scale in perfect, undisturbed balance. On one side of the scale, you have a mixture of things you know, the numbers, and the thing you do not know, the unknown variable. On the other side of the scale, you have another set of numbers. The entire goal of algebra is to gently and patiently isolate the unknown, to strip away the clutter until the hidden truth is finally revealed. Al-Khwarizmi explained that as long as you perform the exact same gentle operation to both sides of the equation, the scale will never tip. It will remain in a state of absolute perfect equilibrium. If you carefully remove a weight from the left bowl, you must simply reach over and remove the exact same weight from the right bowl. If you cut the contents of the left side perfectly in half, you must smoothly and calmly divide the right side in half as well. It is a slow, deeply meditative process of reduction. You are not guessing, you are not rushing, and you are not forcing an answer. You are simply maintaining the balance, step by step, breath by breath, until the complex equation slowly melts away, leaving only a single, beautiful, and undeniable truth resting quietly on the scale. Through his incredibly clear and patient writing, Al-Khwarizmi provided humanity with a set of reliable, step-by-step instructions for solving problems. He showed that you do not need a flash of divine inspiration or the genius of Archimedes to find the truth. You only need a quiet mind, a sense of balance, and a willingness to follow a logical path. In fact, his methodical approach to problem solving was so profound that his very name, translated into Latin as algorithmi, became the root of the word algorithm. Every time a modern computer silently processes a stream of data, or a digital program smoothly guides you to a destination, it is quietly following the ancient, orderly footsteps of Al-Khwarizmi, walking peacefully through the lush gardens of Baghdad. The House of Wisdom transformed mathematics from a specialized tool used by surveyors and astronomers into a universal language of abstract logic. The scholars of the Islamic Golden Age became the dedicated, careful guardians of the world's knowledge. While Europe slept in the shadows of the early Middle Ages, the mathematicians of the Middle East were quietly calculating the circumference of the Earth with staggering precision, mapping the exact movements of the stars, and exploring the deep, mysterious properties of light and optics. They built magnificent, massive observatories on the tops of mountains, where astronomers would sit through the long, cool desert nights, their eyes pressed to brass astrolabes, slowly and silently tracking the eternal rotation of the heavens. They understood that the universe was not a chaotic, frightening place governed by random chance, but a deeply harmonious, mathematically predictable masterpiece. To study equations, to balance an algebraic formula, or to calculate the arc of a celestial body was considered a profound act of spiritual devotion. It was a way of reading the hidden handwriting of the Creator, of perceiving the perfect, flawless order that operates quietly beneath the noisy, chaotic surface of our daily lives. As you continue to rest, sinking heavier and deeper into your comfortable surroundings, let the concept of that cosmic balance wash over you. Imagine the vast equations of the universe, perfectly balanced, completely stable, and quietly holding the stars in their places, ensuring that the sun will rise, the tides will turn, and the peaceful, rhythmic mathematics of reality will continue its slow, beautiful dance through the infinite dark. As the centuries flowed softly onward, turning like the great silent wheels of a watermill in a deep forest, the immense reservoir of mathematical knowledge that had gathered in the Islamic world began to slowly, gently spill over its borders. The knowledge did not move with the sudden, violent crash of a storm, but rather with the slow, inevitable, and peaceful seep of water nourishing dry earth. We drift now away from the lush, fragrant gardens of Baghdad, carried on the warm, westward winds across the Mediterranean, until we reach the sun-drenched, rugged landscapes of the Iberian Peninsula, to the region known as Al-Andalus, or Moorish Spain. Here in magnificent, sprawling cities like Cordoba and Toledo, a beautiful and rare era of peaceful coexistence blossomed. In the quiet, shadowed courtyards of massive libraries, where the air was always cool and the gentle sound of trickling water from intricate marble fountains provided a continuous, soothing rhythm, scholars of different faiths gathered. Monks from the damp, cold monasteries of Northern Europe sat peacefully beside Muslim and Jewish scholars, surrounded by towering stacks of parchment and paper. Dust motes danced lazily in the thin shafts of sunlight that pierced the heavy silence of the reading rooms. These dedicated men were engaged in a slow, meticulous, and profoundly important labor. They were translating the great Arabic texts, the works of Al-Khwarizmi, and the preserved wisdom of the ancient Greeks, into Latin. Imagine the quiet scratching of a sharpened quill, moving steadily across rough parchment, hour after hour, day after day, translating the abstract concepts of algebra and the elegant rules of the Hindu Arabic numerals. Through this quiet, patient devotion, the heavy, restrictive curtain of the Dark Ages began to slowly lift from the mind of Europe, letting in the warm, illuminating light of mathematical reason. But the true awakening of European mathematics required more than just dusty translations locked away in remote monasteries. It required a traveler, a mind that understood the practical, everyday rhythm of the world. In the late 12th century, in the bustling, wealthy maritime republic of Pisa, a young boy named Leonardo was growing up. History would eventually come to know him as Fibonacci. His father was a prosperous merchant and a customs official who directed a trading post in the coastal city of Bugia, located in North Africa, in what is now modern-day Algeria. When Leonardo was still a young man, his father brought him across the shimmering, deep blue waters of the Mediterranean Sea to live and study in this vibrant, aromatic port city. Imagine the sensory atmosphere of Bugia in the 12th century. The air was thick with the scent of roasted spices, dried figs, salty sea spray, and the heavy timber of merchant ships rocking gently at anchor. Here in the lively, echoing marketplaces, young Leonardo was surrounded by traders from across the Islamic world. As he watched them calmly negotiate complex deals, exchanging massive quantities of silk, spices, and precious metals, he noticed something completely extraordinary. These merchants were not struggling with the clumsy, rigid, and unyielding letters of the Roman numeral system that his father used back in Italy. They were not wrestling with the V's, the X's, the L's, and the C's, which made even the simplest multiplication a grueling, frustrating chore. Instead, they were using the beautiful, flowing, and incredibly simple Hindu Arabic numbers. They were using the numbers 1 through 9 and the profound, silent power of 0. Leonardo was absolutely captivated by the sheer elegance and the peaceful efficiency of this system. He realized with a quiet, overwhelming clarity that these 10 simple symbols were the ultimate key to unlocking the true potential of mathematics. They allowed the mind to calculate with a smooth, effortless grace, gliding through complex equations like a skilled ship navigating a calm, open sea. Recognizing the monumental importance of this knowledge, Fibonacci spent the next several years traveling extensively around the entire Mediterranean coast. He visited Egypt, Syria, Greece, and Sicily, sitting quietly with the greatest mathematical masters of the age, absorbing their wisdom like a dry sponge absorbing cool water. When he finally returned home to the quiet, familiar streets of Pisa, he brought this precious, transformative knowledge with him. In the year 1202, he gathered all of his notes, all of his deep understanding, and he wrote a massive, comprehensive book called the Liber Abaci, the Book of Calculation. This was not a purely theoretical, abstract philosophical text meant only for isolated scholars. It was a deeply practical, gentle, and guiding manual designed specifically for the everyday merchants, the bankers, and the tradesmen of Europe. He patiently explained, step by logical step, exactly how to read and write the new numbers, how to smoothly add and subtract, and how to use the magical concept of zero to keep the invisible columns of place value perfectly aligned. He showed them how to easily calculate profit margins, how to convert the bewildering array of different currencies used across Europe, and how to accurately measure the weight of cargo resting in the hulls of their wooden ships. Slowly, but with an unstoppable, quiet momentum, the Liber Abaci began to spread across the continent. It was copied by hand over and over, traveling along the very same trade routes that Fibonacci himself had sailed. As the merchants of Italy adopted the new numbers, their calculations became faster, more accurate, and completely free of the old heavy frustrations. The rigid mathematical darkness of the Middle Ages was gently washed away by a rising tide of elegant, flexible numbers. But Fibonacci gave the world something far more profound and enduring than just a new way to balance a ledger. Hidden within the pages of his great book was a simple, quiet puzzle about the breeding patterns of rabbits. It seemed like an innocent, harmless mathematical exercise. But the specific sequence of numbers it generated would go on to reveal one of the most breathtaking, deeply hidden, and universally peaceful rhythms in all of the natural world. The sequence begins with absolute simplicity. It starts with the number 1, then another one. To find the next number in the delicate chain, you simply add the two previous numbers together. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. Then 8, 13, 21, 34, and so on, spiraling outward into the infinite distance. On the surface, it is just a gentle, predictable progression of addition. But as mathematicians and naturalists began to look closer at the world around them, they discovered a stunning, almost unbelievable truth. This exact sequence of numbers was not just a human invention. It was the silent, underlying architectural blueprint of organic life. Allow your mind to drift away from the numbers on a page and imagine walking slowly into a dense, ancient, and deeply quiet forest. The air is cool, damp, and smells of rich, dark earth and green moss. Look down at a simple pine cone resting on the soft forest floor. If you carefully trace the spiral patterns of the hard wooden scales wrapping around the center, you will find that the number of spirals curving to the left and the number of spirals curving to the right are almost always two consecutive numbers in the Fibonacci sequence, perfectly balanced, usually 8 and 13. Now walk out of the dark forest and into a bright, sunlit meadow filled with towering golden sunflowers. If you look closely into the massive dark center of the flower, where the hundreds of tiny seeds are tightly packed together, you will see the exact same mesmerizing, hypnotic spiral pattern. The intersecting spirals of seeds will perfectly match the sequence, perhaps 34 spirals in one direction and 55 in the other. This peaceful, perfect mathematical sequence dictates the arrangement of leaves on a stem, ensuring that every single leaf receives the maximum amount of gentle sunlight without overshadowing the ones below. It governs the slow, delicate uncurling of a fern frond in the early spring mist. It maps the precise, sweeping curve of a nautilus shell forming in the deep, silent, crushing pressure of the ocean. The further you extend the Fibonacci sequence, taking the ratio of one number to the number that immediately follows it, the closer you approach a profoundly magical, irrational number known as phi, or the golden ratio. It is a number that represents absolute, flawless physical perfection. The golden ratio creates shapes and proportions that the human eye naturally, instinctively finds deeply calming and perfectly beautiful. It is the geometry of pure harmony. As you lie there, breathing slowly and deeply, realize that this ancient mathematical sequence, this quiet rhythm of numbers discovered over 800 years ago, is the exact same rhythm that governs the petals of a rose, the branches of a tree, and the spiral arms of massive galaxies slowly turning in the infinite freezing vacuum of deep space. Mathematics is not just a tool for counting, it is the silent, beautiful poetry of nature, written in the language of perfect, unbreakable proportion. As the calendar slowly turned into the 14th and 15th centuries, this deep human desire to find harmony, proportion, and perfect mathematical beauty began to profoundly reshape the very nature of human perception. We drift now into the heart of the Italian Renaissance, to the beautiful, culturally exploding city of Florence. The Renaissance was a massive collective reawakening of the human spirit. It was a time when the dark, flat, and rigid artwork of the Middle Ages was gently set aside, and artists began to look at the physical world with a renewed, intense, and deeply mathematical curiosity. They wanted to capture the true, breathtaking depth of reality on a flat, two-dimensional canvas, a feat that had eluded humanity for thousands of years. To solve this ancient artistic puzzle, they did not turn to paint or color. They turned to the quiet, absolute truth of geometry. Imagine a brilliant, obsessive architect named Filippo Brunelleschi standing quietly in the piazza directly in front of the magnificent baptistery of Florence. The morning air is crisp, and the rising sun casts long, soft shadows across the cobblestones. Brunelleschi had spent years carefully studying the ancient geometry of the Greeks, and he understood that human vision operates on strict mathematical lines. He realized that as objects move further away into the distance, they appear to shrink at a perfectly predictable geometric rate until they eventually disappear completely into a single, infinitely small dot on the horizon. Through patient, quiet experimentation, Brunelleschi discovered the mathematical laws of linear perspective. He realized that to create a perfect, flawless illusion of three-dimensional depth on a flat surface, every single horizontal line in the painting that recedes into the distance must converge exactly at one single, solitary point on the horizon line. This point became known as the vanishing point. It is a concept of profound hypnotic beauty. A vanishing point is a place of absolute mathematical rest. It is the quiet destination where all the complex, chaotic lines of the world finally meet, converge, and peacefully disappear into the infinite distance. When another brilliant scholar named Leon Battista Alberti formally wrote down the mathematical rules of perspective, providing a step-by-step geometric formula for artists to follow, it changed the world forever. The chaotic, flat, floating figures of medieval art were replaced by deeply serene, perfectly ordered, and mathematically flawless masterpieces. Imagine standing in a quiet, softly lit chapel, gazing up at a massive Renaissance fresco. The arches, the tiled floors, the towering columns. Everything is constructed using perfect, hidden geometry. The eye is gently, inevitably drawn inward, pulled smoothly along the invisible mathematical lines of perspective, sinking deeper and deeper into the painting until it comes to rest completely at the vanishing point. This marriage of mathematics and art brought an unprecedented sense of peace, order, and absolute stability to the visual world. The canvas became a quiet, perfect mathematical universe, completely under the rational control of the artist. The chaotic, frightening randomness of the physical world was tamed by the soothing, unyielding rules of geometry. As you let your muscles relax even further into your bed, sinking down into the softness, imagine your own mind finding its vanishing point. Picture all the scattered, distracting thoughts of your day, all the complex lines of your waking life, slowly extending outward, moving further and further away, growing smaller and smaller, until they all gently converge and disappear entirely into a single, quiet point of absolute stillness on the distant horizon of your mind. Let the perfect, harmonious geometry of the Renaissance bring you a profound sense of inner order, a feeling of deep, mathematical peace that wraps around you as securely and flawlessly as a perfectly calculated archway holding up a starry vault. The vanishing point of the Renaissance canvas gave the human mind a perfect, quiet place to rest, a static and unmoving illusion of reality. But the true physical universe that surrounds us is never perfectly still. The earth beneath you is constantly, silently turning. The dark waters of the oceans are perpetually rising and falling with the gentle, rhythmic pull of the moon. The planets are forever wandering through the vast, cold depths of the night sky. For mathematics to fully understand the grand masterpiece of creation, it had to eventually wake up from the beautiful, static geometry of the ancient Greeks. It had to learn how to capture the fleeting, dynamic essence of continuous motion. It had to learn how to mathematically describe things that never stop moving. For thousands of years, humanity looked up at the night sky and believed, with absolute comforting certainty, that the earth was the solid, unmoving center of everything. The great Greek astronomer Ptolemy had constructed an incredibly complex, massive mathematical system to prove it. In his model, the sun, the moon, and the planets all revolved around our resting world in a series of perfect interlocking circles. But because the planets do not actually orbit the Earth, their movements in the sky often look strange and irregular to ancient watchers. Sometimes a planet would appear to slow down, stop, and drift backward against the backdrop of the stars. To make his Earth-centered mathematics work, Ptolemy had to invent a dizzying, chaotic system of circles within circles, known as epicycles. It was a mathematics of frantic, grinding gears, a highly complicated and anxious system that lacked the deep, elegant peace of ultimate truth. The journey toward a quieter, more harmonious universe began in the cool, crisp air of Northern Europe, in the mind of a quiet, deeply observant Polish cleric and astronomer named Nicholas Copernicus. Copernicus was a man who craved simplicity and mathematical elegance. He spent his long, silent nights looking out of his observatory window, watching the slow, majestic rotation of the heavens. He realized that the chaotic, swirling epicycles of Ptolemy were mathematically ugly and unnecessarily complicated. He proposed a deeply radical, yet profoundly simple shift in perspective. What if we are not the center? What if the massive, glowing warmth of the sun is the true, unmoving anchor of the system, and our world is merely one of many quiet spheres gliding peacefully around it? By mathematically placing the sun at the center of the universe, Copernicus instantly smoothed out the chaotic, erratic motions of the planets. The strange backward wandering of Mars in the night sky was no longer a mathematical mystery. It was simply the optical illusion created when a faster-moving Earth smoothly overtakes a slower-moving planet on the great circular track of the solar system. The mathematics of Copernicus brought a profound, sweeping sense of order to the cosmos. It was a quieter, more elegant universe where the heavy, complicated gears of Ptolemy were replaced by smooth, majestic, and logical orbits. As you rest in the quiet of your room, let go of the need to be the center of your own swirling universe. Allow yourself to just be a quiet, peaceful observer, drifting smoothly along a steady, predictable path, guided by the warm, unseen gravity of a larger harmony. But the beautiful mathematics of the heavens still held one final, deeply entrenched ancient secret that needed to be gently unraveled. Copernicus, much like the ancient Greeks before him, still believed that the planets must travel in perfect, flawless circles. The circle was the geometry of the divine, the shape of absolute perfection. It took the obsessive, lifelong dedication of two vastly different men to finally break the perfect circle and discover the true hypnotic rhythm of the cosmos. Imagine traveling to a small, freezing, and isolated island in the dark waters of the Danish Sound, known as Hven. Here, in the late 16th century, a brilliant, eccentric astronomer named Tycho Brahe built a massive subterranean observatory called Uraniborg, the castle of the heavens. In the bitter, freezing cold of the Scandinavian winter nights, before the invention of the telescope, Tycho and his assistants sat in absolute silence. Using only their naked eyes and giant, beautifully crafted brass quadrants built into the stone walls, they meticulously measured the exact, precise positions of the stars and planets. For decades, night after freezing night, they recorded the silent, sweeping data of the universe with an accuracy the world had never seen. They amassed a vast, silent ocean of numbers, a treasure trove of cosmic coordinates locked away in heavy leather books. When Tycho Brahe passed away, this monumental ocean of data fell into the hands of his assistant, a fragile, deeply spiritual, and mathematically brilliant German scholar named Johannes Kepler. Kepler was a man desperately searching for the hidden music of the spheres, the secret geometric harmony that he believed God had used to construct the universe. For years, Kepler sat in quiet rooms surrounded by mountains of Tycho's data, trying with agonizing patience to force the orbit of Mars to fit into a perfect, flawless circle. He calculated and recalculated, filling thousands of pages with dense, meticulous arithmetic, but the numbers simply would not perfectly align. There was always a tiny, frustrating discrepancy, a gap of just 8 arc minutes, a sliver of the sky so incredibly small it is almost invisible to the human eye. A lesser mind would have simply ignored this tiny error, brushing it away to preserve the comforting illusion of the perfect circle. But Kepler had an absolute, unwavering faith in the quiet truth of the numbers. He realized that the universe was trying to gently whisper a different secret to him. He took a deep breath, let go of the ancient Greek obsession with circular perfection, and allowed the mathematics to guide him into the unknown. He discovered that the planets do not move in perfect circles. They move in ellipses. An ellipse is a slightly stretched, flattened circle, a graceful, elongated oval. This discovery fundamentally changed the rhythm of the universe. In a perfect circle, there is only one center, but an ellipse has 2 distinct focal points. Kepler realized that the sun does not sit perfectly in the center of a planet's orbit. It sits quietly at one of these 2 focal points. This means that as a planet travels along its vast elliptical path, its distance from the sun is constantly, smoothly changing. And this led Kepler to an even more beautiful, profoundly hypnotic mathematical discovery regarding the speed of the planets. Imagine a planet resting at the furthest, coldest edge of its massive elliptical orbit. Because it is so far away from the sun, it moves slowly, languidly, drifting through the dark void. But as its path gently curves and it begins to fall back toward the sun, it smoothly, steadily begins to accelerate. It moves faster and faster as it approaches the immense, glowing warmth of the star. It whips around the sun at its maximum speed, a breathtaking rush of cosmic momentum, and then it is flung back out into the cold, dark depths of space. As it travels further away, it smoothly, gradually begins to slow down, losing energy, drifting slower and slower until it reaches that distant, quiet apex once again, hovering for a suspended, silent moment before the long, slow fall begins anew. Kepler had discovered the true, undulating mathematics of planetary motion. It is a cosmic pendulum, a deeply soothing rhythm of acceleration and deceleration, of speeding up and slowing down, echoing the very rhythm of human breathing. As you inhale, imagine the planet drawing closer, moving with energy and warmth. As you exhale, imagine the planet slowly drifting away, calming down, reaching the quiet, suspended stillness of the deep void. Kepler proved that the universe is not a rigid machine of perfect, unyielding circles. It is a living, breathing, and sweeping celestial dance, governed by elegant, unbreakable mathematical laws. While Kepler was quietly mapping the majestic, sweeping motions of the heavens, another monumental mind was turning his mathematical gaze downward toward the heavy physical reality of the Earth. In the warm, sunlit cities of Italy, a brilliant, rebellious thinker named Galileo Galilei was completely changing the way humanity understood the concept of gravity and falling objects. Before Galileo, the world blindly accepted the ancient teachings of Aristotle, who stated that heavier objects naturally fall faster than lighter ones. It was a belief based on pure philosophical assumption, not on actual physical testing. Galileo was the first to realize that mathematics is not just a language for abstract thought. It is the absolute foundational language of physical reality. To understand nature, you cannot just sit and philosophize. You must measure, you must drop, you must roll, and you must calculate. Imagine a quiet, peaceful afternoon inside the grand, echoing Cathedral of Pisa. The air is cool and smells faintly of old incense. A young Galileo is attending a long, monotonous service. His eyes drift upward toward the high, vaulted ceiling, where a massive, heavy bronze chandelier has been pulled aside to be lit and has just been released. It is swinging back and forth, cutting through the dusty shafts of sunlight in a long, slow, and hypnotic arc. Most people simply saw a swinging lamp. Galileo saw a mathematical puzzle waiting to be unraveled. Because there were no accurate clocks in the 16th century, Galileo reached out and gently placed his fingers against his own wrist, feeling the steady, rhythmic pulsing of his own heart. Using the quiet, dependable beat of his own blood, he carefully timed the swing of the massive chandelier. He noticed something incredibly profound, a hidden symmetry in the physical world. As the chandelier slowly lost momentum, and the wide, sweeping arcs became smaller and smaller. The actual time it took to complete one single swing remained exactly the same. The time it takes for a pendulum to swing is determined entirely by the length of the chain, completely independent of how wide or narrow the swing is. This beautiful, simple mathematical realization eventually led to the invention of the pendulum clock, allowing humanity to finally measure the passage of time with steady, rhythmic precision. Let the image of that slow, swinging chandelier enter your mind. Picture it moving smoothly through the dim light of the cathedral, back and forth, left and right, completely steady, completely reliable. With every slow swing, let your body sink a fraction deeper into your mattress. Let the reliable mathematics of the pendulum guide you into a state of deep, undisturbed tranquility. Galileo took this profound obsession with time and measurement and applied it to the ultimate mystery, how things fall. He built smooth, highly polished wooden ramps, gently inclined them, and slowly rolled heavy, perfect brass balls down the slopes. By rolling them instead of dropping them, he could dilute the intense pull of gravity, slowing down the chaotic speed of the fall so that his mind could carefully observe and measure the mathematics of the acceleration. He discovered a beautiful, flawless geometric rule hidden within the chaos of falling objects. He found that the distance a ball rolls down the ramp is exactly proportional to the square of the time it takes to roll. If it rolls for 2 seconds, it travels 4 units of distance. If it rolls for 3 seconds, it travels 9 units. It was an absolute revelation. Gravity was not just a mysterious, unseen force pulling things downward. It was a strict, mathematically precise engine of acceleration. Galileo beautifully famously declared that the grand book of the universe is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word. He showed that the physical world, from the heavy brass ball rolling on a wooden plank to the massive planets spinning in the dark, obeys a set of quiet, universal numerical laws. As the realization of a mathematical universe slowly took hold of the European mind, the stage was set for a monumental merging of two ancient, separate worlds. For thousands of years, mathematics had been strictly divided into two distinct languages. There was the beautiful visual geometry of the ancient Greeks, the world of shapes, lines, circles, and physical space. And there was the powerful abstract algebra of the Islamic scholars, the world of equations, unknown variables, and the balancing of numbers. They were like two brilliant minds living in the same house but speaking completely different languages, unable to communicate. The man who finally built the bridge between these two worlds, changing the course of history forever, was a French philosopher and mathematician named René Descartes. Imagine a brutal, freezing winter in the early 17th century. Europe is gripped by bitter cold and the chaos of wars. Descartes, a young soldier seeking shelter and absolute quiet, finds a small, heavily insulated room in a village in Bavaria. The room is heated by a massive ceramic masonry stove. It is deeply warm, incredibly quiet, and perfectly isolated from the violent, freezing world outside. It is the ultimate sanctuary for a mind that wishes to retreat inward and find absolute truth. Descartes spent his days in this warm, womb-like environment, simply resting in bed, meditating in profound silence. He decided to strip away every single thing he thought he knew about the world, doubting his senses, doubting his memories, until he arrived at the single, undeniable truth of his own existence. I think, therefore I am. But his meditations did not stop at philosophy. As he lay on his back in the warm, heavy quiet of the room, his eyes lazily traced the cracks and shadows on the blank ceiling above him. According to a famous and beautiful legend, he noticed a single, solitary fly crawling slowly across the flat expanse of the ceiling. Most people would have simply shooed it away. Descartes watched it move. He realized that at any given, frozen moment in time, he could mathematically describe the exact precise location of that fly using only two simple numbers. All he had to do was measure the distance from the fly to the left wall and the distance from the fly to the wall nearest his head. By using two intersecting perpendicular lines, an invisible horizontal axis and an invisible vertical axis, he could pinpoint the exact location of anything in two-dimensional space. This quiet realization in a warm, sleepy room was the birth of the Cartesian coordinate system. It was a stroke of absolute, breathtaking genius. Descartes took the infinite empty void of flat space, and he quietly draped a rigid, perfect, and infinitely expansive grid of numbers right over the top of it. He created a map for the unknown. By laying down this grid, Descartes performed a magical act of translation. Suddenly, a geometric shape could be perfectly described by an algebraic equation. A straight line crossing the grid was no longer just a drawn mark. It was a simple equation showing the relationship between the horizontal x-axis and the vertical y-axis. A perfect circle was no longer just a shape traced by a compass. It was a beautiful, balanced algebraic formula containing the square of the distances from the center. Algebra and geometry were no longer separate languages. They were exactly the same thing, simply viewed through different lenses. This beautiful, unifying grid gave the human mind the power to mathematically graph the invisible. It allowed us to draw the trajectory of a fired cannonball, the slow, curving path of a comet, or the steady, undulating wave of a sound vibrating in the air. Descartes provided the ultimate, infinite canvas upon which all future mathematics would be painted. As you lie in the quiet warmth of your own room, imagine that invisible, comforting grid stretching out infinitely in all directions around you. You are a single, quiet point resting perfectly at the center of the origin, safe, secure, and precisely located in the vastness of space. The chaotic void has been ordered. The lines are drawn. The universe is ready to be mapped. The magnificent grid created by René Descartes provided the human mind with a perfect, infinite canvas. It allowed mathematicians to freeze a geometric shape and describe it with a flawless algebraic equation. But there was a profound limitation to this beautiful system. The Cartesian grid was entirely static. It was a still photograph of the universe. It could beautifully describe a perfect circle or a resting parabola, but it struggled to describe the chaotic, continuous, and ever-changing flow of reality. The universe is not a frozen painting. It is a deep, continuous river of motion. The planets never stop turning, the winds never stop blowing, and the temperature of the air is always imperceptibly rising and falling. To truly understand the cosmos, mathematics needed to learn how to capture the fleeting, ghost-like essence of continuous change. It had to face the terrifying concept of the infinite and the infinitely small, which had haunted the quiet thoughts of Zeno and the ancient Greeks. The profound breakthrough came during a time of great silence and isolation. We travel now to the damp, green, and deeply quiet English countryside in the year 1665. The bustling and crowded streets of London and the busy halls of Cambridge University had been completely emptied by the terrifying outbreak of the Great Plague. A young, fiercely, intensely focused student was forced to pack his belongings and retreat to the absolute safety and total isolation of his family's farm in Lincolnshire, a quiet place known as Woolsthorpe Manor. His name was Isaac Newton. For over a year, young Newton lived in a state of profound, undisturbed quarantine. Imagine the deep, heavy silence of that stone farmhouse. The only sounds were the gentle rustling of the leaves in the apple orchard outside his window, the slow ticking of a wooden clock, and the scratching of his quill by the warm, flickering light of a single candle. In this vast, empty ocean of time and solitude, completely cut off from the noise and distractions of the outside world, Newton's mind expanded into the infinite. He was free to think, to deeply concentrate for days and weeks on end without a single interruption. As you lie in the quiet of your own room, separated from the noise of the day, understand that some of the most beautiful and profound discoveries in human history were born out of exactly this kind of deep, peaceful isolation. Newton was obsessed with the concept of motion. He understood the mathematics of average speed. If you travel in a horse-drawn carriage from one quiet village to another, it is very easy to calculate your average speed over the entire journey. You simply divide the total distance by the total time. But Newton wanted to know something that seemed mathematically impossible. He wanted to know the exact, precise speed of the carriage at one single, frozen, microscopic instant in time. If you shrink the window of time down to an absolute zero, to a single frozen moment, the carriage has traveled zero distance in zero time. And in the strict, unyielding laws of ancient mathematics, dividing zero by zero is a catastrophic impossibility. It is a meaningless void. But Newton was not afraid of the void. He developed a revolutionary new concept that he called fluxions, which we know today as differential calculus. Newton found a deeply elegant way to step right up to the absolute edge of zero without ever actually falling in. He imagined a window of time that was incredibly, infinitely small. So incredibly small that it was smaller than a single grain of sand, smaller than a whisper, smaller than a heartbeat. It was a sliver of time that was almost nothing, but fundamentally, crucially, it was not zero. By using these infinitesimally small ghosts of departed quantities, as they were later called, Newton could calculate the exact rate of change at any given frozen moment. Think of a bird gliding silently through the air. With Newton's calculus, you could mathematically pause the entire universe. You could freeze the bird in midair, suspended perfectly against the clouds, and calculate its exact precise speed and direction in that one solitary millisecond. He gave humanity the power to mathematically tame the chaotic flow of time, breaking continuous motion down into an infinite series of frozen, manageable, and perfectly still frames. While Newton was quietly wandering through his apple orchards in England, independently creating this monumental mathematics of continuous change, another brilliant mind was working on the exact same cosmic puzzle in the quiet, dust-filled libraries of continental Europe. His name was Gottfried Wilhelm Leibniz, a German philosopher, a diplomat, and a man of boundless sweeping intellect. Leibniz approached the great puzzle of the infinite not from the perspective of motion and physics, but from a deep philosophical love of geometry and space. Imagine Leibniz sitting in a grand, quiet library in Paris or Hanover. The walls are lined with heavy, leather-bound books, and a soft, muted light filters through the tall, leaded glass windows. Leibniz was trying to solve an ancient problem that had captivated Archimedes thousands of years earlier. How do you find the exact perfect area of a shape that is completely curved, like the gentle arc of a rolling hill, or the winding, sweeping path of a meandering river? You cannot simply use a ruler to measure a curve. Leibniz solved this by taking the concept of the infinitely small and using it to build, rather than to freeze. He imagined slicing the curved shape into incredibly thin, vertical rectangles. He sliced it thinner and thinner until the rectangles were as thin as a single sheet of paper, and then infinitely thinner still. They became microscopic, infinitesimal ribbons of space. Because they were so incredibly narrow, the curved top of each ribbon was effectively flat and straight. And then, with profound mathematical patience, Leibniz simply added all of these infinite, microscopic ribbons together to find the exact, perfect area of the entire sweeping curve. He called this beautiful process integration, and because he was a man who deeply valued elegance and visual harmony, Leibniz created a new, soothing symbol to represent this quiet gathering of infinite slices. He drew an elongated, gracefully sweeping letter S, standing for the Latin word summa, or sum. To this day, the integral sign is one of the most visually beautiful and calming symbols in all of human language. It looks like the curved hole of a violin or a gentle flowing river winding vertically down a page. When you see an integral sign in a complex mathematical equation, it is an invitation to gather, to accumulate, and to peacefully bring countless tiny, fragmented pieces together into one perfect, unified whole. Leibniz also gave us the gentle, elegant notation of the lowercase letter d, representing the differential, that tiny infinitesimal sliver of change. When you look at the calculus equations written by Leibniz, with their swooping integrals and delicate differentials, they do not look like rigid, cold mathematics. They look like a beautiful, flowing piece of sheet music, a quiet symphony of logic written upon the page. For a time, the world of mathematics was unaware that these two brilliant men, working in total isolation, separated by the dark waters of the English Channel, had independently unlocked the exact same secret of the universe. But the most breathtaking, deeply poetic realization was yet to come. It was the discovery of a profound hidden symmetry that binds the entire cosmos together in absolute balance. It is known as the fundamental theorem of calculus. The theorem proved that the mathematics of Newton and the mathematics of Leibniz were actually two sides of the exact same perfect coin. Newton's differential calculus was all about breaking things down, finding the instantaneous rate of change, and slicing time into infinitely small pieces to find the slope of a curve. Leibniz's integral calculus was all about building things up, gathering the infinite slices of space, and adding them all together to find the area under a curve. The fundamental theorem mathematically proved that these two monumental actions are perfect, exact opposites. They are the ultimate cosmic balancing act. One undoes the other with perfect, flawless precision. It is the mathematical equivalent of inhaling and exhaling, taking apart and putting back together, falling asleep and waking up. This profound harmony meant that the universe was not a chaotic, fragmented place. The concept of continuous change, whether it was a planet falling through the gravitational well of the sun, or a quiet river carving a valley over millions of years, was governed by a deeply balanced, perfectly symmetrical, and totally understandable logic. Calculus provided the ultimate continuous language of reality. It allowed future generations of scientists to mathematically describe the invisible, flowing waves of heat, the unseen propagation of light traveling through the deep vacuum of space, and the slow, rhythmic expansion of the universe itself. The infinite had finally been tamed. It was no longer a terrifying, chaotic abyss that threatened to swallow the logical mind. The infinite had been gently corralled, turned into a powerful, peaceful tool that allowed humanity to map the endless flow of time and space. As you lie resting, breathing slowly and deeply, allow your mind to embrace the quiet, continuous flow of calculus. Think of your breathing as an ongoing, gentle curve. You do not breathe in sudden, rigid, geometric squares. Your breath is a smooth, continuous wave, slowly rising and gently falling. Inhale slowly, feeling the calm accumulation, the quiet gathering of the integral, and exhale smoothly, feeling the slow, peaceful release, the gentle change of the differential. You are a part of that continuous flowing universe, perfectly balanced, resting quietly on the endless, gentle curve of time. The universe described by Newton and Leibniz was a flawless, majestic clockwork, a system of continuous motion where the planets glided along their sweeping, elliptical paths with absolute predictable certainty. With the quiet power of calculus, it seemed that the human mind had finally conquered the physical heavens. If you knew the starting position and the speed of an object, the equations could perfectly predict its future, stretching out into the infinite distance. But down here on the surface of the Earth, away from the perfect, silent orbits of the stars, human life still felt incredibly chaotic. The world was filled with sudden storms, unpredictable harvests, and the random, chaotic tumbling of a thrown die. For thousands of years, humanity believed that chance and luck were entirely wild, untamed forces, governed only by the mysterious, shifting whims of fate or the hidden desires of the gods. To tame the wild, unpredictable nature of chance, mathematics had to learn how to measure the unknown. The Quiet Revolution began in the middle of the 17th century, not in a grand university or a royal observatory, but in the soft, muffled quiet of a Parisian parlor. Imagine a heavy wooden table covered in soft green felt. A pair of small carved bone dice are gently tossed, tumbling over and over, finally coming to a quiet rest in the dim candlelight. A French nobleman with a passion for gambling had a disagreement about how to fairly divide the stakes of an unfinished game. He reached out to a brilliant, reclusive mathematician named Blaise Pascal, who in turn wrote a letter to a quiet, dedicated lawyer, an amateur mathematician living in the south of France, Pierre de Fermat. Through a series of slow, thoughtful letters carried by horse-drawn carriages across the peaceful French countryside, these two brilliant minds quietly gave birth to the mathematics of probability. They realized a profound and deeply comforting truth about the nature of reality. While you can never predict the exact outcome of a single isolated event, like the single roll of a die or the flip of a copper coin, if you zoom out and look at the vast collective picture, the chaos completely disappears. If you roll the dice 10,000 times, the erratic, unpredictable jumps and falls perfectly smooth themselves out into a flawless, unyielding mathematical pattern. They discovered that chance is not actually blind. It is governed by a deep, underlying geometry. They learned to calculate the exact, precise likelihood of any given outcome, mapping the hidden structure of luck itself. This realization eventually led to the discovery of the normal distribution, the beautiful, symmetrical shape known as the bell curve. Imagine a curve that starts low, gently and smoothly rises to a rounded, perfectly balanced peak, and then softly falls back down on the other side, creating a shape of absolute restful symmetry. This single, quiet curve describes almost everything in the natural world, from the heights of trees in a vast forest to the slow, random diffusion of heat in a quiet room. It is the mathematical proof that underneath the noisy, frightening chaos of our daily lives, there is a deep, abiding order. Like dust slowly settling in the still air of an empty room, the random events of the universe always eventually come to a perfect, predictable, and peaceful rest. As the 17th century slowly faded into the 18th, the radiant center of the mathematical world shifted once again, moving away from the mild climates of France and Italy, traveling far into the cold, deep, and heavily snow-blanketed north. We arrive in the grand imperial city of St. Petersburg, Russia. Imagine the city in the dead of winter. The massive winding Neva River is completely frozen solid, a ribbon of pure white ice. The air is bitterly cold, completely still, and filled with the faint muffled sound of horse-drawn sleighs gliding softly over the heavy snowdrifts. Inside the warm, thickly insulated halls of the Imperial Academy, heated by massive, roaring ceramic stoves, lived the most prolific and perhaps the most deeply peaceful mathematician in human history, Leonhard Euler. Euler was a man of boundless, gentle brilliance, possessing a mind that flowed with equations as effortlessly as a bird sings or a river runs. But Euler's life is also a story of profound quiet resilience and the incredible limitless power of the internal human mind. Over the course of his life, a slow, dark shadow began to creep across his vision. First, he lost the sight in his right eye. Years later, a cataract slowly formed over his left. As he aged, the bright, snowy world of St. Petersburg, the faces of his beloved children, and the ink on his parchment slowly faded into a soft gray mist, and finally into absolute total darkness. For most people, the loss of sight would mean the end of a career in a field that relied so heavily on complex written formulas and visual geometry. But for Euler, the physical darkness was not a prison. It was a sanctuary. Stripped of the visual distractions of the waking world, his mind's eye became blindingly, brilliantly clear. He possessed a memory so vast and tranquil that he could hold entire books, complex architectural blueprints, and massive, spiraling algebraic equations perfectly still within his mind. He did not need to see the numbers on a page. He could feel their weight, hear their harmony, and see their glowing, abstract geometry floating peacefully in the dark, silent theater of his own consciousness. Completely blind, he continued to produce mathematics at an astonishing, unbroken pace, gently dictating his beautiful thoughts to his scribes, composing equations much like a master musician composing a flawless symphony completely from memory. Euler possessed a deep, unifying vision of the universe. He was the great harmonizer of mathematics. He was the one who standardized the beautiful, elegant symbols that we still use today, giving mathematics a universal, flowing language. But his most profound achievement was a single, breathtakingly short equation that is widely considered by mathematicians to be the most beautiful, perfect sentence ever written. It is known simply as Euler's identity. To understand its profound, resting beauty, you must first understand the concept of the impossible number. Since the time of the ancient Greeks, mathematicians had stumbled upon a terrifying problem: the square root of a negative number. If you multiply a positive number by itself, you get a positive. If you multiply a negative by a negative, you also get a positive. Therefore, finding the square root of a negative number seemed physically, logically impossible. When René Descartes encountered these numbers, he dismissed them with a mocking, derogatory term, calling them imaginary. For centuries, they were treated as bizarre, frustrating ghosts that haunted the edges of algebraic equations, impossible phantoms that had no place in the physical, measurable world. But Euler did not fear the impossible. He embraced it. He gave this imaginary ghost a simple, quiet name, the lowercase letter I. He allowed it to exist, to flow through his equations, trusting that the pure logic of mathematics would eventually reveal its true purpose. And in a moment of pure, blinding insight, Euler wove this imaginary ghost together with the most fundamental, foundational numbers of reality, placing them all into a single, perfectly balanced scale. Imagine the 5 most important numbers in the universe. First, the number 1, the absolute foundation of counting, the single solid unit of existence. Second, the number 0, the peaceful void, the anchor of nothingness discovered by the ancient scholars of India. Third, the number pi, the eternal, irrational, and flawless geometry of the perfect circle, wrapping around the heavens. Fourth, the letter E, a number representing the slow, continuous, natural growth of organic life, from the compounding of interest to the slow curling of a nautilus shell. And finally, the letter I, the impossible imaginary bridge into a perpendicular, unseen dimension of numbers. Euler combined them into a single, breathtaking line. E raised to the power of I times pi plus 1 equals 0. As you lie in the dark, let the absolute, staggering perfection of that equation wash over you. It brings together the geometry of the ancient Greeks, the continuous growth of calculus, the arithmetic of the Indians, and the imaginary phantoms of algebra, and it perfectly, flawlessly balances them all into a state of absolute, peaceful 0. It is a cosmic chord struck in the dark, a sound of pure, ringing harmony, proving that the universe is not a random, disconnected collection of ideas, but a single, deeply unified masterpiece. The imaginary numbers were not ghosts, they were the missing, silent gears required to make the mathematics of the cosmos turn with absolute, frictionless grace. Today, those once mocked imaginary numbers are the foundational language used to describe the invisible, flowing waves of electromagnetism, the alternating current of electricity that powers our world, and the deep, silent probabilities of quantum mechanics. Euler's vision was not just limited to the infinite and the imaginary. He also found profound mathematical peace in the simple, everyday structures of the physical world. Imagine leaving the grand palaces of St. Petersburg and traveling to the quiet cobblestone streets of Königsberg, a tranquil Prussian city built on the banks of the Prego River. The city was divided into 4 distinct landmasses, all connected by exactly 7 bridges. For years, the townspeople engaged in a simple, relaxing Sunday puzzle. They wondered if it was possible to take a leisurely walk through the city, crossing every single one of the 7 bridges exactly once, without ever doubling back or retracing their steps. People walked the bridges for hours, tracing complex paths, but no one could ever find the perfect route. The problem eventually reached the quiet, blind master, Leonhard Euler. When Euler heard the puzzle, he did not need to visit the city, nor did he care about the physical distance between the bridges or the size of the islands. In his mind, he performed a profound act of mathematical abstraction, a gentle stripping away of all the unnecessary, chaotic details of the physical world. He erased the cobblestones, he erased the flowing water of the river, and he erased the wooden planks of the bridges. He reduced the entire city down to its absolute barest essence. The 4 landmasses simply became 4 small, quiet dots, which he called nodes. The 7 bridges simply became 7 graceful, curving lines connecting those dots, which he called edges. By turning the physical city into a pure, abstract drawing, a network of points and lines, Euler gave birth to an entirely new, incredibly powerful branch of mathematics known as graph theory or topology. He then looked at a simple, quiet drawing and immediately saw the unbreakable, underlying truth. He proved that for such a walk to be possible, every single landmass, except for the starting point and the ending point, must have an even number of bridges connected to it, so that every time you enter an island, you have a separate, unused bridge to exit. Because all 4 landmasses in Königsberg had an odd number of bridges, the perfect walk was fundamentally, mathematically impossible. It was a beautiful, gentle proof. It did not rely on heavy algebra or the strict, rigid measurements of Euclidean geometry. It was a mathematics of pure connection, a study of how things relate to one another in space, completely free from the constraints of distance or shape. You can stretch a topological map, you can bend it, you can twist it like a piece of soft rubber, and as long as you do not tear the connections, The fundamental mathematical truth remains absolutely identical and unharmed. This is the mathematics of relationships. It is the exact same quiet logic that today routes massive streams of invisible data through the global internet, maps the intricate, firing neural pathways of the human brain, and traces the complex and invisible webs of ecosystems. Euler showed the world that mathematics is not always about measuring how far or how fast something moves. Sometimes the most beautiful and profound truths are simply about understanding how we are all connected. As you settle deeper into the softness of your bed, imagine your own mind as a quiet, peaceful network of glowing points. Let go of the rigid distances and the heavy measurements of your day. You do not need to calculate how far you have to go tomorrow or how much weight you are carrying. Just feel the gentle, quiet connections, the soft, undeniable link between your breathing and your heartbeat, the calm, steady connection between the weight of your body and the supportive surface beneath you. Let the tangled, chaotic bridges of your waking thoughts slowly dissolve into a simple, elegant, and perfectly restful pattern guided by the serene, unseen hand of pure logic. For over 2,000 years, the human mind had rested securely and comfortably upon the flat, rigid, and unyielding foundation of Euclidean geometry. Since the days of the great library of Alexandria, the 5 simple axioms of Euclid were considered the absolute, unshakable truths of the universe. They were the flawless architectural blueprint of reality. A straight line could be drawn forever. All right angles were identical. And most importantly, parallel lines would run side by side perfectly straight, infinitely forward into the dark, without ever drifting closer together or moving further apart. This flat, predictable universe was a comforting place. It made logical sense. It aligned perfectly with what the human eye saw when it looked out across a calm, glassy ocean or a vast, empty plain. But as the 19th century quietly dawned, a subtle, profound restlessness began to stir within the deepest levels of mathematical thought. For centuries, scholars had been quietly bothered by Euclid's 5th rule, the rule of parallel lines. It lacked the crisp, undeniable simplicity of the other 4. It felt less like a universal truth and more like a human assumption. Countless brilliant minds had spent their entire lives sitting in candlelit rooms, trying desperately to prove that the parallel postulate was an absolute necessity, trying to weave it flawlessly into the rest of the geometric tapestry. But the postulate always resisted. It stood apart, a quiet, lingering mystery waiting in the shadows of the ancient texts. The shattering of this flat, rigid universe did not happen with a loud explosion, but with a slow, deeply peaceful realization that blossomed independently in the minds of 3 different men, separated by thousands of miles of quiet European landscape. In the misty, heavily forested mountains of Germany, there lived a man named Carl Friedrich Gauss, widely known as the Prince of Mathematicians. Gauss possessed a mind of such staggering, effortless brilliance that he often saw the answers to incredibly complex problems instantly, as if they were suddenly illuminated by a flash of silent lightning. Far to the east, in the vast, open steppes of Russia, a quiet, deeply dedicated professor named Nikolai Lobachevsky was working in total isolation. And in the heart of Hungary, a passionate, brilliant young army officer named János Bolyai was obsessively pondering the exact same ancient puzzle. Through deep, silent meditation, these 3 men arrived at a thought so radical, so deeply counterintuitive, that for a long time Gauss completely refused to publish his findings, fearing the world was simply not ready to hear it. They asked a beautifully simple question. What if Euclid was wrong? What if the universe is not perfectly flat? What if the invisible grid of space itself is allowed to gently bend, to warp, and to curve? They realized that if you simply remove the rigid rule of parallel lines, the entire structure of mathematics does not collapse into chaos. Instead, it smoothly and beautifully expands into an entirely new, deeply exotic, and limitless landscape. They gave birth to non-Euclidean geometry. Imagine in the quiet theater of your resting mind, taking the flat grid-like canvas of the universe and allowing it to gently warp downward, curving smoothly into the shape of a massive infinite horse's saddle or the flaring, elegant bell of a brass trumpet. In this strange, breathtaking new world, known as hyperbolic space, the ancient rules of reality gracefully melt away. If you draw 2 parallel lines in this curved universe, they do not stay safely beside each other. As they travel forward into the infinite distance, the very fabric of space gently pushes them apart. They curve smoothly and infinitely away from one another, drifting further and further into the endless dark void. In this universe, if you draw a massive triangle, the angles inside it will not add up to the perfect, comforting 180 degrees of Euclid. They will add up to less, the lines bowing inward, pulled by the strange, unseen geometry of the void. A few decades later, another brilliant German mathematician, a quiet and physically frail man named Bernhard Riemann, took this concept and gently bent the universe in the exact opposite direction. He asked us to imagine a geometry that wraps completely around the surface of a massive, perfect sphere. Imagine standing on the equator of a gigantic, silent world. You and a companion stand a few miles apart, both facing completely true north. You are standing on parallel lines. As you both begin to walk straight forward, perfectly parallel to one another, you move up the curve of the massive globe. You never turn toward each other, you simply follow your straight line. Yet as you approach the silent, icy peak of the North Pole, the very curvature of the planet slowly, inevitably draws you together until your lines peacefully and perfectly intersect at the absolute top of the world. In Riemann's spherical geometry, there is no such thing as a parallel line. Every single straight path, if extended far enough, will eventually curve gently around the universe and intersect with every other path. It is a geometry of ultimate cosmic connection. It is a closed, finite universe, beautifully wrapped in upon itself, where nothing is ever truly isolated, and every journey eventually leads back to a point of quiet intersection. Legend tells us that Gauss, in his deep desire to know if our physical universe was flat or curved, actually attempted to measure the geometry of reality itself. He climbed to the quiet, freezing peaks of 3 different mountains in the German region of Hanover. Using massive, highly polished mirrors, he reflected blinding beams of sunlight across the vast, misty valleys, creating an absolutely massive, miles-wide triangle of pure light floating in the quiet air. He meticulously measured the angles of this triangle of light, searching for even the slightest deviation, the tiniest whisper of curvature. The results were perfectly flat, perfectly Euclidean. But the seed had been planted. The human mind now knew that space was not a rigid, unyielding box. It was a soft, flexible fabric, waiting for the right force to bend it. As you lie resting, allow your own mind to gently release the need for flat, rigid, and uncompromising rules. You do not need to walk in a perfectly straight line. Your thoughts do not need to fit into perfect, rigid squares. Allow the mental space around you to become soft, flexible, and deeply yielding. Let your thoughts drift along gentle curves, wrapping smoothly around the peaceful geometry of your dreams, completely free from the strict boundaries of the waking world. Just as the rigid, straight lines of classical geometry were beginning to beautifully bend and curve, the mathematical mind prepared to take its final, most breathtaking, and deeply philosophical leap into the unknown. It was time to completely tame the ultimate mystery. It was time to look directly into the boundless, terrifying void of infinity and learn how to count it. For all of human history, from the ancient Greeks to the brilliant minds of the Enlightenment, infinity was treated as a vague, misty, and philosophical concept. It was simply a word used to describe a process that never, ever stops, like counting upward without end, or drawing a line that never reaches a destination. It was seen as an endless horizon, a concept of potential, but not something that could be held, measured, or treated as an actual, completed mathematical object. It was too vast, too overwhelming for the human mind to grasp. But in the late 19th century, a deeply philosophical, highly sensitive, and profoundly brilliant mathematician named Georg Cantor decided to walk quietly and fearlessly into that endless horizon. Cantor developed a new elegant language of mathematics known as set theory. A set is simply a collection of things. It could be a set of physical objects, like a collection of smooth stones resting on a beach, or a set of abstract concepts like all the even numbers in the universe. Cantor realized that you do not need to actually count the items in 2 sets to know if they are the exact same size. He reached back 40,000 years, returning to the very first primitive mathematical thought of humanity, the concept of one-to-one correspondence. If you have a massive, quiet theater filled with seats, and every single person in the room sits down, and there are no empty seats left and no people standing. You instantly know without counting a single number that the infinity of the people exactly matches the infinity of the chairs. They are perfectly paired. With this gentle, deeply peaceful logic, Cantor began to pair up the infinite sets of the universe. He started with the most familiar infinity, the natural numbers, 1, 2, 3, 4, rolling on forever like a slow, steady drumbeat echoing into the dark. He called this a countable infinity. You could spend the rest of eternity quietly counting them one by one. Then Cantor did something that shocked the mathematical world. He asked, what about the fractions? What about all the numbers that exist in the spaces between the whole numbers? Between the number 1 and the number 2, there are an infinite number of fractions. 1.5, 1.25, 1 1/8. The space between every single number is packed infinitely dense with more numbers. Surely the infinity of all these densely packed fractions must be vastly, overwhelmingly larger than the simple, marching infinity of the whole numbers. But Cantor, using a beautifully elegant diagonal drawing, proved that he could perfectly pair every single fraction in the entire universe with a whole number. He wove a single, continuous, sweeping thread through the dense matrix of fractions, proving that despite their overwhelming density, they were exactly the same size as the counting numbers. It was a profound mathematical illusion. The infinity of the fractions was completely, peacefully tamed, neatly paired up, and organized into the exact same endless, rolling drumbeat. But Cantor did not stop there. He looked deeper into the quiet, continuous flow of the mathematical river. He looked at the real numbers, the numbers with decimals that stretch on forever without repeating, like pi or the square root of 2. The deeply irrational numbers that had so terrified the ancient Pythagoreans. He asked, can these numbers be paired up? Can they be counted? Through a masterpiece of logic known as the diagonal argument, Cantor proved something so profound, so deeply mind-altering, that it completely shattered the foundations of human logic. He proved that no matter how you try to arrange them, no matter what infinite list you create, there will always be real numbers left over. They slip through the infinite net. They cannot be paired up. He discovered that the infinity of the real numbers is vastly, incomprehensibly, and heavily larger than the infinity of the counting numbers. He proved that infinity is not just one single, massive, dark abyss. There are different sizes of infinity. This single discovery cracked open a breathtaking, awe-inspiring view of the mathematical cosmos. Cantor revealed an infinite hierarchy of infinities, nested one inside the other, rising upward forever like a majestic, never-ending, and perfectly silent staircase ascending into the absolute dark. He gave these magnificent, towering infinities a name, using the first letter of the Hebrew alphabet. He called them the Alephs. Aleph naught was the quiet, countable infinity of the whole numbers. Aleph 1 was a vastly larger, uncountable ocean of infinity. And beyond that, an endless, towering sequence of Alephs, each one infinitely larger than the last, stretching out into a realm of pure, staggering abstraction. The mathematical universe was no longer just a limitless expanse. It was an infinitely deep, infinitely rich ocean, filled with depths that the human mind could barely fathom. It proved that the universe of numbers is far grander, far heavier, and infinitely more profound than the physical reality we can see and touch. As you lie deeply enveloped in the quiet of the night, let the profound, majestic weight of Cantor's infinities gently settle over you. You do not need to understand the vastness of the universe. You do not need to count all the stars in the dark sky or measure all the grains of sand upon the earth. The universe is infinitely detailed, possessing a depth and a scale that goes on forever, larger than large, deeper than deep. You are simply a quiet, peaceful point of consciousness, floating effortlessly in that endless, magnificent ocean. Let the unmeasurable, unbreakable continuum of reality support you. Let go of the need to count the moments. Sink deeply into the uncountable, boundless, and perfectly silent infinite, and allow the gentle waves of eternity to carry you peacefully into the dark. The vast, towering hierarchy of infinities discovered by Georg Cantor left the mathematical world in a state of profound, breathless awe. For a brief, fleeting moment at the dawn of the 20th century, It seemed as though the human mind had finally mapped the ultimate boundaries of logic. The abstract realm of numbers felt like a massive, completed cathedral, its spires reaching infinitely upward into the dark. In the year 1900, as a new century quietly unfolded, a brilliant and deeply optimistic German mathematician named David Hilbert stood before a grand, hushed assembly of scholars in Paris. The air in the lecture hall was thick with anticipation, filled with the soft rustle of formal coats and the quiet scratching of pencils. Hilbert, possessing an unshakable faith in the power of human reason, laid out a masterful, sweeping vision for the future. He presented a list of 23 unsolved mathematical problems, a quiet, peaceful roadmap for the next 100 years of human thought. Hilbert firmly believed in a concept known as absolute formalism. He believed that mathematics could be transformed into a flawless, mechanical game of symbols, played by perfectly rigid, unbreakable rules. He dreamed of a mathematical universe where absolute certainty was guaranteed. He declared, with a calm and deeply comforting authority, that in mathematics there is no such thing as the unknowable. Every single mathematical statement, he argued, must be capable of being proven either absolutely true or absolutely false. His famous, ringing words were, "We must know. We will know." For decades, the greatest minds in Europe dedicated their lives to fulfilling Hilbert's beautiful, orderly dream, attempting to build a foundation for mathematics so solid, so deeply rooted in pure logic, that it could never, ever be shaken. Imagine sitting in a quiet, softly lit study in the ancient, fog-draped city of Cambridge, England. The room smells of old leather bindings and burning pipe tobacco. Here, two brilliant philosophers, Bertrand Russell and Alfred North Whitehead, spent years locked in a grueling and meticulous labor of love. They wrote a massive, dense, 3-volume masterpiece called the Principia Mathematica. Their goal was to gently trace every single mathematical truth in the universe, all the way back to just a handful of simple, undeniable logical axioms. They were trying to capture the infinite and lock it safely inside a perfect, unyielding cage of logic. It took them over 300 pages of dense, painstaking, and heavily symbolic proofs just to definitively prove that 1 + 1 = 2. But as Bertrand Russell was quietly weaving this flawless tapestry of logic, he noticed a tiny, almost invisible loose thread. It was a subtle, lingering flaw in the very concept of sets, the very foundation of Cantor's infinities. It is a paradox that is often explained using a simple, peaceful story about a village barber. Imagine a quiet, isolated town where the rule is that the town barber shaves all those and only those who do not shave themselves. It is a simple, logical rule, but the quiet mind must inevitably ask, does the barber shave himself? If he does shave himself, then according to the rule, he must not. But if he does not shave himself, then according to the exact same rule, he absolutely must. This is known as Russell's paradox. It is a gentle, endless loop, a snake quietly eating its own tail. When applied to the deep, fundamental logic of set theory, asking about a set that contains all sets that do not contain themselves, it completely shattered the illusion of a perfect, flawless mathematical foundation. The tiny loose thread, when gently pulled, caused the entire massive tapestry of absolute certainty to slowly unravel. Russell later wrote that the discovery of this paradox hit him like a physical blow, a sudden dark cloud drifting over his perfectly ordered, sunlit world of logic. However, the ultimate, most profound humbling of the mathematical mind did not come from Russell, but from a quiet, shy, and intensely introverted young Austrian logician named Kurt Gödel. In the vibrant, bustling, and intellectual atmosphere of Vienna in the 1930s, Gödel lived a life of deep, solitary contemplation. He was a man who rarely spoke, preferring to let the quiet, unyielding power of numbers speak for him. At the incredibly young age of 25, Gödel published a paper that would completely, permanently, and beautifully change the way humanity understands the nature of truth itself. Gödel found a way to turn the immense, rigid machinery of mathematics against itself. He invented a brilliant, deeply elegant system known as Gödel numbering, where he could take any mathematical statement, any logical rule, and translate it perfectly into a single massive number. Mathematics could suddenly talk about itself. Equations were no longer just describing geometry or arithmetic. They were actively describing their own structural limits. Through a masterpiece of flawless, undeniable logic, Gödel constructed a mathematical statement that essentially said in the quiet, absolute language of numbers, this statement cannot be proven. Let the profound weight of that idea gently settle into your mind. If the statement is false, then it can be proven, which means the entire mathematical system is broken, contradictory, and chaotic. Therefore, the statement must be absolutely undeniably true. But because it is true, it means that it can never, ever be proven within the system. With this single brilliant stroke of logic, Gödel completely dismantled David Hilbert's dream of absolute certainty. He proved his famous incompleteness theorems, demonstrating that in any complex logical system, there will always be profound, beautiful, and absolute truths that simply cannot be proven using the rules of the system itself. Mathematics is not a closed, perfectly sealed box. It is an open, infinitely expanding, and fundamentally incomplete landscape. No matter how deep we dig, no matter how vast our equations become, the universe of numbers will always hold secrets that are mathematically, permanently beyond the reach of human proof. Rather than a source of anxiety, this realization is one of the most deeply soothing and liberating concepts in all of human thought. It means that the universe is infinitely richer and more mysterious than any rigid set of rules could ever capture. It proves that perfection is an illusion, and that absolute certainty is simply not required to appreciate the immense sprawling beauty of reality. As you rest in the quiet dark, let go of the heavy burden of needing to know every answer. You do not need to prove your existence. You do not need to perfectly calculate your path through life. The universe is wonderfully, eternally incomplete, leaving endless room for mystery, for wonder, and for the quiet peace of the unknown. While the logicians were quietly discovering the boundaries of abstract thought, a momentous shift was occurring in the realm of physics, drawing pure mathematics back down from the philosophical heavens and weaving it directly into the physical fabric of the cosmos. We travel now to a quiet, unassuming patent office in the city of Bern, Switzerland, in the early years of the 20th century. Here, a young, softly spoken clerk named Albert Einstein spent his days reviewing technical drawings of clocks and mechanical looms. But his mind was resting quietly on a much grander stage. He spent his long, silent hours daydreaming, imagining what it would be like to ride smoothly and effortlessly alongside a beam of pure light, racing through the dark vacuum of space. Through these deep, meditative thought experiments, Einstein realized that the ancient, rigid universe described by Isaac Newton was fundamentally flawed. Newton had believed that time and space were like a massive, invisible, and completely empty wooden stage, a rigid, flat box where the events of the universe simply played out, completely unaffected by the actors within it. A second ticking by on a clock on Earth was exactly the same as a second ticking by on a distant star. Space was flat and time was absolute. But Einstein's equations slowly revealed a universe that was profoundly, beautifully flexible. He discovered that space and time are not separate, rigid things. They are woven together into a single, seamless, and deeply elastic fabric known as space-time. In this new universe, time is not a steady, unyielding drumbeat. If you travel faster, smoothly accelerating through the dark void, time itself gently slows down, stretching out like a piece of soft taffy. Einstein's former mathematics professor, Hermann Minkowski, provided the perfect geometric loom to weave this new reality. He created the mathematics of four-dimensional space, combining the three physical dimensions we move through, up and down, left and right, forward and backward, with the fourth flowing dimension of time. In Minkowski's geometry, our lives are not just a series of isolated, fleeting moments. They are solid, continuous, and completely unmoving shapes woven permanently into the vast, silent block of the space-time continuum. But Einstein was not finished. He wanted to understand the ultimate, unseen force that holds the planets in their orbits and keeps our feet planted firmly on the ground: gravity. For years, he struggled to find the right mathematical language to describe a gravity that was not just an invisible, pulling rope, but a fundamental property of this newly discovered space-time fabric. The flat, comforting geometry of Euclid, with its perfectly straight lines, was completely useless to him. He needed a mathematics where the invisible grid of the universe was allowed to warp, to sag, and to beautifully curve. He reached out to a mathematician friend, Marcel Grossman, asking for help, desperate to find the right geometric tools. Grossman quietly reached back in time, opening the dusty, theoretical textbooks of the 19th century. He pointed Einstein toward the deeply abstract, seemingly useless spherical geometry developed by Bernhard Riemann decades earlier. Riemann had simply been exploring the pure philosophical concept of curved space, never intending for his equations to actually describe the physical world. But in a moment of profound cosmic poetry, the deeply abstract thoughts of a quiet, frail German mathematician turned out to be the exact, perfect, and flawless language required to read the physical blueprint of the entire universe. Einstein used Riemann's curved geometry to create the general theory of relativity. He showed that massive objects like the heavy, glowing sphere of the sun or the solid, quiet mass of the earth do not simply pull on other objects. Instead, they rest heavily upon the soft, flexible fabric of space-time, creating deep, smooth, and sweeping valleys in the geometry of the void. Imagine a perfectly flat, tightly stretched trampoline in a quiet, dark room. If you gently place a heavy bowling ball in the absolute center, the fabric smoothly sags downwards, creating a curved depression. If you then take a small, smooth marble and roll it across the fabric, the marble does not travel in a perfectly straight line. It follows the invisible, curved geometry of the sagging fabric, rolling smoothly in a circular orbit around the heavy center. This is exactly how gravity works. The Earth does not orbit the sun because it is being pulled by an invisible chain. It orbits the sun because it is simply following the most natural, peaceful, and perfectly straight path it can find through a universe that is fundamentally smoothly curved. Gravity is not a force. It is the physical shape of the cosmos itself. As you lie in your bed, feeling the weight of your own body resting heavily against the mattress, understand that you are not being pulled downward by a harsh, invisible force. You are simply resting in a quiet geometric valley created by the mass of the Earth. Your body is gently following the flawless, unyielding curvature of space-time. Let that thought bring you a deep, physical sense of peace. You are perfectly supported. You are cradled in the sweeping, curved architecture of the universe itself. The mathematics of the cosmos is not just an abstract idea written on a chalkboard. It is the very fabric that wraps around you, holding you securely, safely, and peacefully as you drift endlessly through the quiet dark of the night. While Einstein was wrapping the macroscopic universe in a smooth, continuous blanket of curved space-time, other brilliant minds were peering downward into the absolute smallest, most hidden fragments of physical reality. They looked deep into the microscopic heart of the atom, fully expecting to find tiny, perfect planets orbiting tiny, perfect suns, following the same reliable, predictable rules of calculus and gravity. But the mathematics of the quantum world was not smooth, and it was not continuous. It was a strange, vibrating, and deeply mysterious realm that completely defied human intuition. Brilliant physicists like Max Planck and Niels Bohr discovered that energy does not flow in a steady, unbroken stream like water from a pitcher. Instead, it moves in tiny, discrete, and indivisible packets known as quanta. It is a universe built of impossibly small, sudden steps, a reality that flickers rather than flows. In this strange, microscopic landscape, a quiet, brilliant German physicist named Werner Heisenberg introduced the uncertainty principle. This was a profound, earth-shattering mathematical law proving that you can never, ever know both the exact position and the exact momentum of a particle at the exact same time. The more fiercely you focus your mathematical lens to pinpoint exactly where a particle is, the more its speed and direction fade away into a soft, blurry haze of probability. It was the ultimate, undeniable mathematical proof that the universe fundamentally demands a certain level of mystery. You simply cannot rigidly control, predict, or perfectly measure the foundational building blocks of reality. They are not solid, unyielding marbles waiting to be counted. They are quiet, shimmering waves of potential, resting peacefully in a state of overlapping possibilities until the very moment they are observed. Let this profound quantum uncertainty be a deeply comforting thought as you rest. You do not need to know exactly where you are and exactly where you're going at every single moment of your life. It is perfectly natural and mathematically proven by the universe itself to exist in a gentle, unstructured state of undefined potential. Allow your tired mind to completely release its heavy grip on absolute certainty. Let go of the rigid need to predict tomorrow. Simply float in the quiet, overlapping waves of probability, trusting that you are exactly where you need to be in this frozen, unmeasured moment. As humanity began to mathematically understand these deepest, most confusing layers of physics, the ancient logical engine of mathematics was quietly preparing to completely transform the physical world one final time. In the hushed, highly secretive, and heavily guarded rooms of Bletchley Park in England during the mid-20th century, a brilliant, softly spoken mathematician named Alan Turing was dreaming of a completely new kind of machine. For thousands of years, mathematics was an abstract philosophy that happened entirely within the human mind, or was painstakingly, slowly written down on clay tablets, papyrus scrolls, and parchment paper. Turing imagined something radical, a machine that could physically embody the abstract, invisible rules of human logic. He conceptualized what is now known as the Universal Turing Machine, a theoretical device that could read a simple, infinite strip of paper, follow a rigid set of mathematical instructions, and perfectly simulate the logical processing of the human brain. Turing proved that all of human mathematics, all the vast, towering complexities of calculus, geometry, and algebra, could ultimately be broken down into a simple binary rhythm, true or false, on or off, 1 or 0. With this profound, elegantly simple realization, mathematics completely left the dusty, yellowed pages of history books and entered the modern digital realm. The computer was born, a physical architecture of pure, humming logic, capable of performing billions of complex calculations in the blink of an eye, completely free from human emotion, distraction, and fatigue. With the incredible, tireless, and unyielding power of these new digital minds, mathematicians were finally able to look at the universe through a completely different lens. For the first time in history, they could feed simple, repeating equations into a computer and let them run over and over millions of times, just to see what would happen. And what they discovered was a breathtaking, hypnotic, and endlessly fascinating new world known as chaos theory and fractal geometry. A mathematician named Edward Lorenz, while quietly studying the flowing, complex equations of global weather patterns, discovered the butterfly effect. He found that in massive dynamic systems, a change so incredibly tiny that it is almost unmeasurable, like the gentle, silent flap of a butterfly's delicate wings in a distant, humid jungle, could mathematically ripple outward, compounding and growing through the equations until it completely alters the massive, violent path of a hurricane weeks later. The mathematics of chaos prove that the universe is so deeply, infinitely connected that every single microscopic action truly matters. But within this apparent swirling chaos, another brilliant mind named Benoit Mandelbrot discovered an ocean of unbelievable, organic beauty. He graphed a simple, looping equation on a computer screen, creating what is now famously known as the Mandelbrot set. It is a shape of infinite, staggering complexity. When you look at the fuzzy edge of this mathematical shape and mathematically zoom in, you do not find a smooth, straight line like the edge of a drawn circle. You find beautiful, swirling, curling tendrils. If you zoom in again, magnifying the image a million times, you find the exact same beautiful, swirling shapes repeating themselves perfectly, spiraling downward forever into the infinite microscopic depths. Fractals prove that the rough, chaotic, and seemingly random shapes of the natural world, the jagged, uneven edges of a towering mountain range, the intricate branching pathways of a human lung, the ragged, sweeping coastline of a massive continent, and the delicate branching veins of a single green leaf, are all fundamentally governed by a deep, perfectly repeating mathematical order. The universe does not build the world by hand. It uses simple, elegant, repeating equations to quietly, patiently grow its most complex and breathtakingly beautiful structures. Reality is simply a fractal, a pattern repeating itself endlessly on every conceivable scale, from the swirl of a galaxy to the curl of a fern. And now we have finally reached the end of our grand, sweeping journey through the long, quiet corridors of time. We have traveled together from the warm, flickering amber light of a prehistoric campfire, where the very first human mind sat in the dark and carefully carved 29 simple, counting notches into a piece of weathered bone. We have drifted across the massive, flooding banks of the ancient Nile, through the quiet, shaded olive groves of classical Greece, and into the rich, fragrant, and deeply spiritual translation halls of the House of Wisdom in Baghdad. We have watched the flat, comforting universe of Euclid slowly and beautifully warp into the curved, elastic space-time of Albert Einstein. And we have peered into the infinite digital landscapes of modern computers, graphing the fractal edges of reality itself. The story of mathematics is not just a history of numbers, symbols, and cold equations. It is the ultimate, profoundly poetic story of the human spirit. It is the story of our deep, abiding, and desperate desire to find peace, order, and absolute harmony in a universe that so often feels chaotic, random, and overwhelming. Mathematics is the quiet, invisible thread that binds all of human history and all of physical reality together into one unified masterpiece. It is the universal language of the cosmos, a language spoken fluently by the spinning, majestic galaxies, the slow, rolling ocean tides, the swinging of a brass pendulum, and the microscopic, unseen vibrations of the atom. It is a language that requires no translation, for its truths are eternal, its logic is unyielding, and its structure is fundamentally, heartbreakingly beautiful. Now, as the heavy, comforting blanket of the deep night completely surrounds you, it is time for your own restless mind to finally come to a perfect mathematical rest. Let all the complex, chaotic equations of your life slowly fade away into the dark, empty corners of your room. Let the endless, looping numbers of the day, the worries, the plans, and the calculations dissolve completely into the peaceful, comforting, and absolutely silent void of zero. You are a small, quiet, and perfectly balanced point of consciousness, resting safely at the absolute center of an infinite, deeply ordered universe. There are no more problems you need to solve tonight. There are no more distances you need to measure, and no more unknowns you need to balance. There is only the gentle, rhythmic rising and falling of your chest, a smooth, continuous wave perfectly synced with the slow, eternal, and silent turning of the cosmos. Sink deeper and heavier into the softness beneath you. Let the perfect circles, the smooth, sweeping curves, and the absolute, unbreakable harmony of the mathematical universe wrap around you like a warm, protective, and eternal embrace. The long journey is over. The numbers are finally silent, and the deep, restorative, and infinite darkness is gently calling you home. Sleep now. Drift away into the infinite, peaceful quiet of the void. Sleep.